科跟，比如说那个任正非任总也有一个非常有意思的一个关联哈。我觉得其实很多年前，我们跟国内跟政府官员跟大众去解释什么是统计学的时候，有时候还蛮费劲的哈。老是说，哎呀，你们是不是统计局造假数据的？是吧？实际上我们这个就是当然统计局现在做的其实很好了，然后我们学科也做得很好。但我想前几年的话呢，我想那个任总在接受央视采访的时候讲了一句非常重要的话，他说这个人工智能实际上就是统计学。那我想实际上这句话的话呢，我觉得实际上对整个国内统计学的这个推广呀，对大众的认知，我就起到了一个非常非常重要的作用哈。我想我们面向未来吧，我们也非常希望我们这个清华的统计系啊，包括我们的这个全国的统计学同仁，能够和我们的业界啊和 AI 其实保持更密切的这种合作跟关联哈。然后我们一块儿共同努力啊，把这个统计数据科学和人工智能的发展，进一步的往前去这个推广。Yeah, so Edo, the Shin, so I'm a little bit sorry. So we have two official languages, and Chinese and English. Yeah, sometimes when we go to Chinese, you can ask your buddy nearby for help. I think they can provide English translation service for you guys. Okay, so yeah, 我们再次感谢这个我们这个来自业界的支持哈，然后还有芮祥林博士。Yeah, OK. 好哈，那下面的话，我们一个这个简短的我们的open ceremony as is over. So now let's switch to the keynote talk. 我们第一个这个session 是由这个中科院院士陈松溪老师来主持。Yeah, let's welcome Professor Song Xi Chen from our department chair and member of national.
All right, it's a great pleasure to introduce Wen as the first keynote speaker. Wen is professor of statistics at Stanford University, also a professor of biomedical data science. He's a member of U.S. National Academy of Sciences, and also Academic Sinica, and also Academic of Science of Hong Kong. Wen has worked extensively in mathematical statistics, Bayesian statistics, and computational biology. He's really truly a leader in statistics and interdisciplinary area of statistics. And he has educated a strong set of graduate students, including Jun here, and also we have Li Cheng on the other side of the street, who joined Peking University. I would like to spend a few minutes on Wen's support on Chinese statistical development in the last 15 years. So 16 years. 2009, and the Peking University decided to invest some money on statistics by establishing a statistical center. But at that time, the university was not sure what to do with it, whether it's be together with applied mathematics or separate statistics. So the provost, Lin Jianhua, had a meeting in Berkeley of president of universities around the Asian Pacific. And he asked me and Bin Yu to organize a small panel to justify it, to how to develop statistics in Peking University. And Wen comes, all right? So that's a September day in Berkeley. Wen drive from Stanford, and then we spend like 2 hours in the women's college, I remember. And so we have very intensive discussions, and then we have lunch there. And then in the afternoon, we have another 2 hours with like Biko and Rice and Zheng Qingshui all come. And so at the end of the day, the provost Lin decided, we should have a statistical center at Peking University. After that, so the center was established in 2010, July, and Wen was the chair of the International Advisory Committee. So that's for 9 years where I was the director. So Wen worked very hard. So I remember we have the review of 3 years. So Wen was the chair, and then after 2 days of review, intensive review, we all go to see opera, Chinese opera. But Wen decided to stay in Boya to finish the report to the university the next day. So, this is only one example to show the dedication of Wen to development of statistics in China. I noticed Wen is also a member of an international committee of Tsinghua's Statistical Research Center. But anyway, so I'm really grateful. And the Provost Lin constantly, talk about you. And so we are grateful. Today, without further ado, Wen today will talk about Bayesian statistics and deep learning. Let's welcome.
Thank you, Xiongxi, for that wonderful introduction. I think that the founding of the Tsinghua Department of Statistics and Data Science is really a milestone event in Chinese statistics, and I think also statistic community of the whole world, because this would, for sure, would ensure an ever-increasing number of some of the best and brightest students in China can have the opportunity to pursue statistics as their major field of study. And I think that would definitely have a big impact on the development of the field of statistics worldwide. So congratulations on the first anniversary, and we've all been waiting for this milestone event to happen, and it did happen at last. So today I just want to share with you some recent result, mainly the work of my current PhD student, Sophia Lu, on the use of deep learning tools on a very classic statistical problem, which is approximate Bayesian computation. Okay. So just some general remarks about the development of statistics and AI. I think historically, idea from the field of statistics has impacted development of AI very significantly. In terms of formulations of problem, and some theories on convergence, on algorithms, stochastic approximation, and so on. These are all sort of fundamental to the development of machine learning in general, and how to evaluate performance and so on. So these are classic concepts that emerge from the field of statistics. Now, but more recently, with the intensive investment on AI, we now have a set of new tools that's emerging from the field of AI. And these include, very flexible, expressive classes of functions and highly efficient algorithm that we can use to learn from really huge data sets, and use extensive use of embedding and so on. So this set of tools are, I think, going to be very useful, not just for solving the kind of problem that current AI researchers are focusing on, but in fact they may be used to attack some classic statistical, traditional mainstream statistical problem, such as causal inference, such as density estimation, and so on. So today I just want to give an example of this in the area of Bayesian inference. So approximate Bayesian inference was first proposed by Simon Tafere and his co-workers when they are looking at some problems that arose from the field of phylogenetics. So in that set of problem, it is easy to simulate data, but very difficult to compute or evaluate the likelihood function. So all the traditional tools that we use for Bayesian inference, such as importance sampling, Markov chain Monte Carlo, just cannot be used. So they formulate this very simple approach of getting to get an approximate sample from the posterior distribution. The posterior distribution is of course the quantity of interest in Bayesian inference. So it's very simple. They assume that you can draw the parameter value theta from the parameter space. So you have to have a generative prior distribution. And you have to know how to generate data given that parameter value. So with this, you can now repeatedly generate pairs of theta and x. So with a large set of theta and x value generated this way, if you only pick those x, pick only those theta values whose corresponding x value, the corresponding data, is close to the observed data. Right? So this neighborhood with radius epsilon, if epsilon is small, then that means that parameter value is generating a data that is close to the observed one. And if you reject all the other theta, but only keep that set, then of course you are getting the conditional probability of theta, given that the data is close enough to your observed data. So that would give you an approximate sample of theta from this conditional distribution, which is very close, should be very close to the conditional distribution of theta given that value of x, right? So that is a very simple kind of rejection sampling idea. Of course, the problem with this approach is that when the data is high dimensional, which is typically the case nowadays, the chance that you would find a x value that is close to the observed x is very small. Right? If the parameter space is a unit cube, unit cube in 10 dimensions, and you want a neighborhood whose linear dimension is 1/2, which is not really very close, right? The chance of that happening is 1/2 to the 10th power. So it sort of decreases exponentially as the data dimension increases. So this concept cannot be applied directly. And what people have been doing is to, instead of using your original data x, you compute a summary statistic, S of x. S of x is, you want it to be low dimensional. And you also want it to be informative. So the best is, of course, to have a sufficient statistic. But without a likelihood, how do you know what is a sufficient statistic? So a lot of proposals to construct summary statistic has been developed. I just want to give you one example. This is work by Jiang Bai, who was a PhD student of mine. And in his thesis, he was looking at this method of constructing the summary statistic. Basically, from the pair of theta and x value, you can now, by non-parametric regression or by standard machine learning method, try to learn an estimate of the conditional expectation of theta given x. So this is, of course, a estimate of that, and is a statistic, right? And typically in classical Bayesian inference, theta is low dimensional, x is high dimensional. So this conditional expectation would be a good summary statistic. Basically, it's informative about the mean of the distribution. So I would call this a mean sufficient statistic. So ideally, you would want to use the true conditional expectation as a statistic. But since we don't actually know this, but we have a lot of samples of theta and x, so we can learn to estimate it. Right? So the estimated conditional expectation will be our sufficient statistic. And this tend to work quite well when the distribution is kind of unimodal and shape. So this was spelled out in this paper. So in his thesis, he used neural network as the estimate for the conditional expectation, and so that was sort of like my first serious use of neural network in sort of this direction, a reverse direction of using it to solve classic statistical problem. And so this network, really can capture very highly nonlinear dependency. This is a simple example. If you take a 100 high-dimensional observation of basically a lattice of spins, right, up and down. And this is the classic Ising model. And we actually know what is the sufficient statistic in this case, right? Is this sum of the products of neighbors. You can try to assess this approach by seeing whether from this repeated simulation of theta and x, you can in fact estimate the correct. So this S star is the known sufficient statistic, it's the theoretical one, right? And this S of x is the one that you learn by fitting a simple neural network, multi-layer neural network. And you can see that it does capture, the variation pretty well, except for this, last bit where there's a, high curvature. So if you use your inference, use S of x to do the conditioning, you would get a pretty, decent approximation. So let's look at this concept in more detail. So what we were doing, in Jiang Bai's thesis was that we are trying to come up with a neighborhood, A epsilon, around the observed data that has the property that if you condition on this neighborhood, you would get a good approximation to the conditioning on the observed data. And this suggests that we use M of x, which is the conditional expectation, as the statistic, summary statistic. And since it is not known, we will try to estimate it using machine learning. Okay. So that's the logic. Now, of course, this objective of trying to guarantee that the conditional mean is close to the true conditional mean, is desirable, is necessary, but not sufficient. What you want is the whole distribution to be close, not just the mean to be close, right? So in examples such as this one, which is a classic example in the field of approximate Bayesian computation. So the data is generated from a normal distribution whose mean and covariance depends on theta, where theta has the prior, which is just uniformly distributed. So this is a highly multimodal posterior. If you look at the posterior, it has this kind of shape. So what's the point of insisting that the mean is close, right? The mean is not really the informative thing. It's the whole distribution. So in Sophia Lu's thesis, we are trying to tackle this problem. And the starting point is to say, if you want the whole distribution to be close, you may want to choose a particular distance function in the space of distributions, in the space of posterior distribution. So I use the notation pi sub x to mean a posterior distribution conditional on x as the observation. Right? So you look at all the possible value of your data, and you want to select those whose distance, whose posterior distribution, corresponding posterior distribution, is close to the posterior distribution based on the true observation. Right? So if that is the case, then if you use the acceptance criteria that this rho of x, right? This just depends on x, because x observed is fixed in the Bayesian analysis. So you can just omit x off and look at this as a function of x, and you want to estimate this function as a function of x. So that is our task. So here, phi sub x is the posterior conditional on x, and d is the distance in the space of posterior distributions, and rho hat is the estimate of that ideal function, rho of x. So that's the sort of the general approach. So the technical question we need to solve is which distance function to use. Right, this is a distance function in the space of distribution. You have to choose it very carefully. And then once you have chosen your distance, how to estimate this function rho of x. And you want to estimate from this repeated pair of theta and x value. And then finally, what kind of threshold you use to determine whether to accept or reject. So let's look at the first question, which distance function to use. So we are proposing to use a distance that is derived from the one-dimensional Wasserstein distance. So let's use this notation. W tilde to mean the Wasserstein distance for univariate distributions. So if you have a pair of distribution u and v, and since they are univariate, so there is a corresponding two quantile function, q1 and q2. Right? So mu1 and mu2 are two distributions, and q1 and q2 are their corresponding quantile function. These are univariate distributions. So if delta is 0, then you just get the LP log of the quantile functions. That is the Wasserstein distance. The Wasserstein distance is derived by coupling of two distributions, but in univariate distribution, it reduces to that. Okay? And usually, you would want to trim away some probability at the two ends so that the distance becomes more robust and you can handle it. It's less sensitive to outlier. So this is kind of a truncated versions of the Wasserstein distance. Now, so let's extend this to multidimensional distributions. What you want to do is to take a random projection. So phi here is just a random direction. You sample from the unit sphere. Once the direction is fixed, you can project it in one dimension and compute the corresponding univariate, the Wasserstein distance, along that projection. And then you average over the unit sphere. Right? This is called a slice Wasserstein distance. And as a metric, is equivalent to the standard Wasserstein distance. Right? And but we feel that the projection on the coordinate axis are particularly important because they're more interpretable. So we want to take a convex combinations of these marginal projections as well as the average over all the directions in the unit sphere. So this is the distance we want to use. And I'll explain why. Because computing distance for multivariate distribution is very difficult. But because of this relationship, computing distance for univariate distribution is much easier. So we want to rely on this slicing idea. So the other thing is that we don't want to actually have to average over all the random directions. We can use a Monte Carlo estimate by sampling k random directions and then compute the corresponding one-dimensional Wasserstein distance. And that will give you a Monte Carlo estimate of that average over the whole unit sphere. Right? So this is the quantity you need to compute. So altogether, there are k random directions that you use. K is chosen by you. D is the dimension of the parameter space. And so k pi is equal to k plus d is the number of such integral that you need to evaluate. These integrals involve the quantile functions. So if you use a trapezoidal rule to approximate this integral, let's say you use h plus 1 percentage points to compute this integral, then if you know the quantiles at this regular grid of fractions, then you will get an approximation to this integral. So this whole thing reduces to learning those quantiles. Right? So let's look at the situation. So we are using rho hat of x as the criteria. This rho hat of x is the estimate of the distance between the posterior distribution based on x and the posterior distribution based on observed data. To estimate that distance, you need to estimate for each random direction, you need to have h plus 1 quantile points for that projection, and you have k pi directions. Okay. Yeah. This is drawing. Okay. This is going back. I want to go back to that page that I.
No, that's the go forward, go back.
Which one is forward?
That's go back.
This is back.
Go back.
Okay.
Yeah, right?
Okay, we're here. Yeah. So this is it. Okay.
Keep on.
Okay. Okay.
Yeah.
Oh, okay. Good. Yeah. Okay. So. So putting this all together, the problem we have in front of us is for k pi directions, for each direction we need to estimate h plus 1 quantiles. Right? So we let this set of quantile, we denote it by this q of x, right? Because the posterior distribution depends on x. So we basically need to estimate a k pi times h plus 1 dimensional function of x, which will represent the quantiles that we want in order to evaluate those integrals. So fortunately, there has been tools developed in the AI world for this task. And so we are taking advantage of that. So in this paper, in PMLR, they were proposing to extend the classic technique of quantile regression method, which is a standard sort of econometric statistical method for doing regression using quantiles. And they extend it by replacing the linear function by neural networks. So they call this implicit quantile network. And you do this by using a loss function to fit the quantile. So this goes all the way back to Hilbert's work, and there are many ways to create loss functions, which, when you feed your data using this loss function, by minimizing this loss function, you get contacts. Right? The typical example is if you minimize using the absolute error loss, you get the median, right? And if you weight the positive and negative differently, then depending on how you weight it, you get different contacts. So this is basically the same idea, except that instead of using linear regression, you use a neural network here. Now remember, we are putting all the losses together with all the direction, all the percentage points. So this is a large sum. It's a function of the weight of the neural networks. And you can then apply the standard tools to optimize it, right, using atom optimizers and mini-batch and so on. So this is the formulation of the problem. This is a step where we rely on these new tools from AI to solve this classic problem. Any question? So the quantile functions are not fit one by one. They're fit jointly. So one network with a very high dimensional input, which is the data, right? And then the output is this k prime times h plus 1 output. And then there are many hidden layers in between, depending on your architecture. Okay, so the last question is, how do you choose epsilon? Well, in fact, there's no one value of epsilon that will work in all situations, because if epsilon is too small, then you have very high rejection rate. It's very inefficient. But if epsilon is too large, you don't get a good approximation, right? Because the label is not small. So instead, we'll use an adaptive idea. You start with a large value for epsilon, and then based on what you get there, you decrease your epsilon, so on. So it's kind of like an annealing of the distance. Okay? So specifically, let us use this notation. Given an epsilon value, given a prior alpha, you have learned a rejection region or acceptance region using the previous, the method in the previous slides. So this region is just this, right? Is your estimate of the distance based on this prior. So you start using the prior that you actually want to analyze as your initial prior. And then you carry out this generation of theta and x data pair, a large number of them. And then you estimate that slice-Rosenstein distance to get your acceptance criteria using that prior. Right? Now, once you have accepted those theta, you basically have a sample from this conditional distribution. Right? So this conditional distribution is based on using pi, the original prior as the prior. And because epsilon, initially epsilon 1, is large, this is not a very good approximation for the true posterior distribution of theta given x op. So you want to decrease your epsilon. Now, because although this is not a good approximation for the true posterior, it's still better than the original prior, right? So now you go back and replace the prior by this updated prior. And you repeat this. And hopefully that prior will concentrate the x values, the theta and x values, so that you are much more likely to accept with a smaller threshold. So step by step, you get better and better approximation. Okay. Because the epsilons are decreasing, this probability with epsilon equal to epsilon 1, that event is a superset of the corresponding event when you decrease epsilon. Right? So this monotonicity is important. So this turned out to guarantee that at each stage of the iteration, you will have a reasonable acceptance probability. Right? Whereas if you start right off with a very small epsilon in order to get a close approximation, you get an exponentially small probability. But that problem is eliminated if you choose epsilons correctly. Okay, so the last technical point is that in step 3 of the iteration, in order to iterate this algorithm, you would need to have sample from this prior after one step, right? So, but the situation is that you only have a sample from this distribution. That the accepted value is a sample. So from that finite sample, you need to generate more theta from the same distribution. So this is basically generated modeling in AI. So you can achieve this by any of a number of tools, such as generative adversarial network, or variational autoencoder, or in this particular work, we actually use this penalized optimal transport network that Sophia also developed. It's based on optimal transport theory. It seems to be, it's kind of related to the GAN, but it's more efficient using the optimal transport as a kernel for the calculation. Okay, so let's now look at the examples. We can return to this multimodal example that I just showed you, and we compare this new method, which we call adaptive Bayesian inference, to the classic ABC method using the Wasserstein distance in the data space instead of the space of posterior as the accept-reject criteria. So this is the standard way of using Wasserstein distance. So our innovation is that we are using the Wasserstein distance in the space of posterior distribution. That turned out to be a key. Yeah. But this is so many people are using this, and we want to compare it. And then we can also use this mean sufficient statistic that I just discussed, second one. And then there are these two new methods are not ABC methods, but they are based on using neural network to approximate the likelihood. So now you're trying to approximate the likelihood instead of the posterior. And so we want to compare to all of them. And these are some sort of details of the implementation, architecture, and so on. So in this particular example, there are these parameters. There are actually 5 parameters. And you can see that in the marginal distribution, many of the methods did not get the bimodality, right? But a few of them get. So I think if you look at all this picture, ABI definitely is doing quite well. And I think SNLE, the neural likelihood method, also seemed to do well in this case. But the other method just fell. Fell in one of the, at least one, it fell miserably in at least one of the marginals. I also want to point out that iteration is important for the good performance. So in our new method, with only one iteration, you do not get a very good approximation, right? Especially for theta 2. But you go to the next iteration, it improves a lot, right? So this is another example, also, a pretty standard example in this field. So this is a highly nonlinear kind of time series model with 4 parameters. And again, comparing the same methods, same set of methods. Now, in this data set, it turned out that previously SNLE was doing very well, but in this example, it's not doing well, right? Goes like that. Yeah. And the ABI method continued to do well. Yeah. Yeah, so this is still not perfect. Yeah. Here we only have 3 iterations. So we haven't tried. We should investigate more. Yeah. It's a lot better than the other methods. Yes. Yes. Which is good, right? The whole idea of ABC is to do a lot of computing. Just to generate a lot of data and expert is a lot of computation. But then you replace thinking by computation, which is good. So this is a classic example. It's called the Lotka-Volterra dynamic, which is a ODE that is used often to model predator and prey. And in actual application, you go and sample the number of animals, and it's always a count data. So the more faithful model would be based on a Markov jump process. It's a birth and death process. But the process has this dynamic, right? So the number of prey would decrease if y, the number of predator increases and so on. And so you translate that dynamic into the birth and death rate, and then you get this self-equation. So this is how we generate the data. So you can simulate this Markov jump event rate. And so you can simulate it very easily if I give you the rate. Now, but what is the data? If you observe the continuous trajectory, then everything is easy. But you never do that. You only have a finite set of time in which you go in and do the survey. So your observed data is a sampling of the continuous trajectory. And based on that observed data to compute the probability is very difficult. That involves integrating over all the trajectories. Right? So this is a classic situation where it's very easy to simulate, but very difficult to evaluate the likelihood. So these are some of the trajectories. And again, you can apply these methods. And again, several of them do very poorly, but some of them okay. But ABI continue to do well here. Okay, so we have many more examples, but this is just a selection of examples. So this is very different from the kind of AI, the scenario when AI is applied typically. Because here we have a situation where the parameter is really of interest. So in conclusion, I like to make a remark that is somewhat philosophical, which is that in this era of deep learning and large language model, many students in my Bayesian class ask me, what is the role of Bayesian inference in this era of large language model? Because in this model, the parameter, the weights that define the network, they are not really of interest. Just use it to get some function, right? And why should I care about the posterior distribution? So that's valid. Often we don't want to care about doing Bayesian analysis of posterior distribution. When the parameter is is not of intrinsic value. But there are many, I claim that there are many areas, especially in the natural sciences and the social sciences, when there is deep domain knowledge that is embedded into the model. Like for example, in this predator and prey analysis, another example is, of course, the original example, the phylogenetic analysis that motivated the development of ABC. Another set of examples that come to my mind is from cosmology. People have theory-based models for how galaxies are formed and so on, and they have these observations, and it's easy for them to simulate, but the likelihood is impossible to compute. So in those situations, the parameter is directly connected to the underlying science, and you really care about them. And what you are interested in is in the current set of experiment or the current data set. So these are high-value data set because you are performing or collecting this particular data just to answer some specific questions about the parameter. And you really care about the answer. In that situation, you want to do Bayesian analysis. And if you're in a situation when you cannot deal with the likelihood, then we have shown that it turned out that this deep learning and AI methods are useful. So it sort of comes full circle, come back and impact on statistics. So I'll end here. Thank you.
Quantile Hoover loss. How did you derive quantile Hoover loss from /Wasserstein?
Yeah, so that loss function is just like the absolute error loss function. So
it's a classical one, right?
Yeah, there are several ones that you can use, but the Hoover loss function robust, so we use that. Yeah, so it's basically like the absolute error loss, but with a smoothing here at the origin, so they don't have that. Always just like that. And depending on the quantile, you can. Yeah.
Thank you.
Other questions?
Yes.
But we struggle the overfitting problem in neural network because it easily get overfitted. Then how did you deal with that?
Overfitting. Well, you.
So if we naively use over-parameterized the neural network, then the quantile, like with the width between 95% and 5%, quantile is going to get narrow and narrow.
Yeah, so I have to admit that we did not actually work seriously on the quantile network. We are using a tool that has been published, right? And we rely on that to fit the quantile network. And so all these examples are using the tool in that paper, the PMLR paper. We didn't innovate on the underlying AI method. We are using the existing AI method to solve a statistical problem.
More questions? Yes, Edo.
So first of all, I want to say this is really thank you. This is really the first example I see of use of AI tools within a very principled statistical framework, which makes me very happy. And the results are great. So my question is about the simulation, right? ABC and I guess ABI and all these computational methods are very computationally expensive. So in the simulation, did you set a budget for computation, and are all the methods that you compared
Yeah.
within the budget, or how do they compare to each other in terms of,
They are all based on the same number of pairs of theta and x that has been simulated. So some method does not require iteration. So they
can use more pairs?
So all the method use, let's say, 15,000 samples of theta and x. Right? So that one is said to be uniform across all methods. But of course, each method may have additional computation. Fitting the quantile network may be more expensive than some other part, but we didn't try to take that into account.
Okay, well, thanks.
I have a question.
Yes.
So you talk about the role of the scientific models for the Bayesian learning, for the theta, which is the model of the, from the science or social sciences.
Yeah.
How about for the parameter from the neural network? Is there any way you can also learn those hyperparameters?
Well, so the standard AI approach is to just optimize and try to get the optimal weight. And that's it. It's very rare that people will try to worry about the uncertainty in inferring this network weight, because those weights don't actually mean anything. Mm-hmm. They are not really identifiable. They are there as a tool to get a function.
So this is not, it's outside of the Bayesian inference.
Yeah, so I would say Bayesian thinking is not useful for that kind of problem. Those parameters are not interesting.
All right, okay, so we can, we can talk to Wen after talk. Okay, let's thanks Wen for the wonderful talk. Yeah.
欢迎大家回来。就我们继续我们今天上午的这个主旨报告。我是清华大学统计数学科学系的杨立坚。那么接下来由我来主持孙茂松教授的主旨报告。孙茂松教授呢，是我们现在担任我们人工智能研究院的常务副院长。孙茂松教授也是在这个 digital humanity 方面，对我们这个统计学科的这个在这个交叉学科的这个应用啊，做了很多的支持。我记得好几年前我们一起就是一起这个评审过我们这边的一个重点项目。大家可能不一定都知道，就是我们有一个人工智能的这个诗歌的这个写作创作系统，叫做九歌。这个也是在孙茂松教授的这个领衔下，在我们这个就是这个 natural language processing 这个实验室，做出来的。我让我的孩子们都使用过那个系统，就是真的是能写的诗，你是看不出是这个人工智能写出来的。孙茂松教授呢，也是我们曾经担任过清华大学计算机技术与科学系的系主任和党委书记，也是我们这个中国的这个 ACL 的 Fellow， 也是欧洲科学院，就是这个Academy of Europe 的外籍院士，然后在我们国内的这个就是这个 language processing Chinese language translation 方面做了大量的这个服务和这个原创性的科研。现在我们就欢迎孙茂松教授来给我们做报告。
谢谢杨老师的这个介绍啊，这个In fact, I feel very nervous talking here. You know, my opinion is, you know, I graduated from Tsinghua, okay, but the statistics courses in Tsinghua, I think, at the undergraduate level, is not so deep and systematic. So my training on statistics is, you know, is just at the preliminary level. So I feel very nervous. Yeah. But Professor Liu asked me, you need to talk about something on large language model or something. So 勉为其难 in Chinese 勉为其难 okay. You know, my research field is in natural language processing, that is using computer to understand natural language. At the beginning of my career, you know, it's late 1980s of last century. Everything is rule-based. Okay, I read a lot of books, linguistic books. So you had to know, I mean, morphology, knowledge, syntax, semantics, discourse, and something like that. Read a lot of books. But later on, I found, especially in the deep learning era, all the books, for an engineering point of view, totally no use, useless, totally useless. But for your training is for Xin, as Professor Zhu said, for the training of Xin is good, but for engineering point of view, totally useless. Yeah. And in the mid of 1990s, the paradigm shifted to statistics based. Okay, so we know we use Mark model, hidden Mark model, maximum entropy principle, supported by the machine, and LDA, the topic model. So a lot of things I think are borrowed from statistics, but we simply use it as tools. Okay, but in the 2010, roughly, everything changed again. It seemed all the methodologies we used before that in the deep learning era, it seems most of most of them become useless in engineering, in engineering point of view. Okay, so it's not easy for us. Okay, we change for time to time. Okay, so and the AI change too fast. So every day, as you wake up, you feel changes. So in AI community, with performance of your model is the number one, regardless of what theory, no matter what theory you use. This area, performance is number one. Okay, so we have to run every day. Okay, no time to think about something deep. Okay, so my talk in general will be very shallow. Okay, so that's why I talk about a lot on the background. Okay, so this is some amazing phenomena or strange phenomena of large AI models, in particular large language models. Okay, and all of this call for deep research, in particular in statistics. Okay, given this context. Okay, large language models definitely is stochastic. It's statistics. Okay, so the one sentence can describe large language model. We use net token prediction. Okay, no net token prediction. So given context, okay, left context, the model try to predict the probability distribution of next word. So that's just one sentence. So it's a conditional probability, or given a left context. It's totally statistical, yeah. But the problem here is, you have dice, you have 6-sided dice, but here, the size is unlimited. Given any, the length can be arbitrarily long. Okay, so that the size of the dice is infinite, almost infinite. At each point, you have many choices. So that depending on the size of your vocabulary. So it's unlimited context multiply vocabulary size. So that's it seems from classic statistics, it's impossible to get such a probability distributions reliable. It's impossible. Okay. At least for me, I think it's impossible. But you look at the performance of large language models, it does this. Okay, it does this. It can generate fluent any sentences, given fluent sentences. Okay, almost at any time. So that problem have solved. So given a limited side of dice, you can get the proper distribution. So that's not easy, I think. So compile, it's very complex, okay. So how large language model, how does large language model do this? So it's very simple, in fact, okay, it's very simple. So the key is, so that we know transformer architecture. So we have layer, several decoder blocks, multiple layers. The key is, so for example, given us, this is a generative model, so give a sentence, so robot So the sentence, the robot must obey the orders given by human beings. Or we want this model to generate this sentence. So robot must obey. So next word is orders. Okay, you predict is orders. So the key is, first, we don't regard words as discrete symbol. We use vector. Okay, we use vector. So that's called representation learning. Representation. Okay, we use representation of this one. Another is called the attention. So attention is, for example, here, we use obey to attend, must to attend a robot. The mechanism is very simple, just dot production. Okay, you get a width. So in fact, we get a vector here. Vector here. It's the weighted average of all the three vectors. So using that vector, we use softmax or something like this to produce the probability of this one. So the key is vector representation. Then you can, so no longer how long you have, simply by weighted average, you can solve this problem. So it's yeah, this vector, or this vector. And every layer, the vector is processed where a nonlinear transformation. Okay, a lot of nonlinear transformation. So so I think about a term. Is this vector-based statistics? Vector-based. Everything is not based on discrete symbols. It is based on vector. Okay, so I don't know if the term is good or not, but it seems it may be a new branch. Okay, for statistics. Okay. So we are now from everything in number. It's a word of Pythagoras, okay, 2,500 years ago, okay, to the era of deep learning, okay, so these three guys are Turing Award winners, okay, push deep learning into practice. So everything is a group of numbers. Everything is vector, okay, we are facing such a era, we are in such an era. So the vector, why the vector? I give example. So if machine can prove, the model can prove the cat is walking in the bedroom, but the vector, no, cat, dog, similar. Okay, walking, running are similar, bedroom, room are similar. So it can easily to understand the dog was running in the room, even though the model haven't seen this example before. Okay, so that's the principle. So if you look at the vector of the vocabulary automatically learned by the model, okay, you can see. For example, text, words, languages are grouped together automatically. Okay, so this is adverb. Okay, this is mental or ourself, herself, themselves, himself. So syntactically they group together. Okay, and even so, the word. Quen has two meanings. It can group automatically two meanings. Okay, so and you can even find some patterns. Okay, between vectors. So for example, so a famous example is king. The vector of king minus vector of man plus vector of women, it's equal to queen. Okay, so some patterns between words can be automatically found. Okay. So vector-based statistics. So I think I'm confusing. Okay, for the large language model. So it processes huge text corpora. But if you ask him the frequency, for example, of statistics in this model, they don't know. They don't have absolute frequency of any words or any n-grams. They don't have that. I'm strange. Why they ignore this one? So without absolute frequency, you think your feeling is you are in the sky, not on the ground. Okay, so it's given a sentence. It's easy to calculate the probability of that any given sentence. But if you give a fragment of sentence n-gram, you don't have you cannot find the frequency of it in the model. Okay, so without you just have conditional probability. But for Bayes' law, so frequency is important. Okay, frequency is important. So that may have some impact on using Bayes' law. And another issue I think we need to pay attention is, so network prediction, that means its distribution is also unlimited. So at any time step, okay, it can change dramatically. For example, I eat, yesterday night I eat, you can say meal, the distribution is the probability, meal, dinner, or something like this, okay. But if you say last night I eat a Beijing duck will turn to the first. So every position, a certain position, the distribution of network may change very dramatically. So it's almost infinite. So what's the characteristic of this probability distribution? How to sample the network given that probability? I think the research on this aspect is very preliminary. Okay, we randomly sample the words according to its probability distribution. Okay, but if you sample high frequent words, general sentence will be fluent, but lack of novelty. If you sample low-level words, you may have some problem in fluency, okay, but you may get more novelty, okay. And given a time series, at which point, some point may, if you ask a model to write an article, some point, some choice of words may influence the whole structure of the article. But at other points, maybe majority point, it just changed some nuance, okay, detailed. So how to choose the point, the turning point in the time series in a series of network prediction distribution is still, I think, deserve our deep attention. So a lot of things I think we can do research here. So vector-based statistics. Okay. Next, I feel very confused. Okay, about some phenomena. Okay, amazing phenomena. No, the AI community just observe such phenomena, but no solution. We don't know how to explain this. So amazing phenomena one is deep double descent. Also, it's a work of 2019 roughly. Okay, not so not very new. So by Harvard University and OpenAI, okay. So the point here is, so this is the model complexity. This is the performance of the model performance. So common knowledge in machine learning is you cannot underfitting, you cannot overfitting. Okay, so if your model is too big, given the fixed data set, okay, the empirical error will be continue. I mean, the error in training data set will continue to decrease, but its prediction capability will get worse. But this work found. So this is this one. Okay, but if you continue to increase the model size, the error decrease again. Okay, so that's called double error design. It's very strange, but why we don't know. Okay. Another amazing phenomenon is proposed by GPT-3. Okay, the paper is language model are few short learners. It's also very strange. You know, one shot, for example, for machine translation. Okay, you just give instruct, so translate it into French. Oh, this is task description. Then give one example, so say author, so error. This is French translation. Give one example. Then you can input any English sentence. Error. Then it translates. Okay. You know, I have carried out machine translation for many years. Usually, so in the statistical model, we need to prepare bilingual corpora, align bilingual corpora very carefully. So you send English part into encoder, and you get the French translation from decoder. But here, that paper say you needn't prepare corpora, parallel corpora. You just collect corpora from web, no matter what formats they may have. Okay, it's very strange. Then you just give one example. Give one example, then it can do high quality translation. So this is amazing. At that time, I asked my students, so that paper is very long. You know, the deep learning large language model paper usually 70 pages, so very long. So I read it, fast read it, and I ask students to check if they use bilingual corpora. My student answered no. They doesn't mention that. So that one is very interesting. It's very interesting. Okay. That's called in context learning or context learning. So if you ask large language model who won the 2014 World Cup, so GPT-4 response. So if without one example, okay. This is correct. Germany won the FIFA World Cup, and Germany. So he may add something not relevant. Okay. So this is 废话. Okay, in Chinese 废话. Okay. But if you give that prompt, answer the question using the format, so you give one example. So you defeated Argentina in the final. It was a slow scoring game. Then you ask who won the World Cup in 2018. Okay, so the answer will be correct. So it will exactly follow that pattern. It's also very strange. Okay, so you know the things are relevant, but still two different things. But it can follow the pattern. Of just give one example, so it's also strict. Okay. So that's a task trivial QA. So by GPT-3 paper, so green line is given one, we call one shot, give one example, okay. So the dotted line is trained with large human annotated data, okay. So just give one example, if the model is small, performance is 5%, okay. But you don't change the algorithm, you just increase the model size and accordingly the size of data set, okay. When it reaches this one, it's comparable to human intensively annotated data or performance, so that's the strange. Amazing phenomenon 3 is also you increase the model. For some difficult task, you increase the model size. At the beginning, improvement in performance is small, but across some critical point, it increases dramatically, okay. In particular, in the task, the so-called chain of thought prompting, chain of thought. Chain of thought is also very strange, okay. Unbelievable. For example, you gave a standard prompt, so input, for example, to solve some mathematical problem. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? This is a mathematical question, so you give the answer directly. So the correct answer is 11. Then you ask a new question, new mathematical question. Cafeteria has 23 apples. You can see some changes compare this, not exactly the same situation. The output, if you use it to this one shot to give the model, the answer will be correct, 27, okay. But if you give some detail, for your cafeteria has 20, no. That's mathematical question. So Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, okay. Then you 5 plus 6 is 11. The answer is 11. So you give some the procedure of solving problem. Then you give that question again, another question again. In that case, you will get the answer will be correct. So that's called the chain of thought. But if you look at the chain of thought, very strange. So you know, this one, you can say this one in this way. Another person can say this thing in another way, okay? It's not in mathematical form, okay? Mathematical logical form. It's just in natural language. But it seems the model can understand this okay, properly, okay? So it's very free, okay? Expression is very free, okay? And these two things, this one and the question 1, question 2, literally it seems quite different. You can also process it, okay? So this chain of thought also very amazing. Amazing phenomenon 3 is, this is an example given by Google, okay? So when the model is small, it can process maybe 10 tasks. When the model grows, it can solve maybe 100 tasks. You don't need to give extra training, okay? Just use same algorithm. But the model increase, the data also increase, okay? You need to change the algorithm. So all of these, I think, are amazing. We found it. We found this phenomena in large language models, but without explanation. We don't understand why. So A common judgment is this is emergence. Okay, that's correct. But the problem is why and how emergence occurs. We don't know. Okay, so that deserves deep attention. So scaling law. So Professor Zhu mentioned scaling law. There are two ways. So if you use large language model, big data, or a big model, still scaling law. But Professor Zhu used small data, so that's another technical line. Okay. But for large language model, even in this area, we have a lot of thinking. Okay. For example, Judy Pearl is a Turing winner, Turing Award winner. His opinion is what is the scientific principle by which foundation model in large models can circumvent the theoretical limitation of data-centric method as we know them. So his opinion is large language is not deep. Okay, what problem you solve? Okay, but Yan LeCun, another Turing Award winner, believe this one is a right way. Okay, to realize AGI. But recently his opinion changed. Okay, not always this one. Okay, so we have a lot of struggle. Okay, even in this field. Okay. Large language is not perfect. A lot of problems. For example, this is a recent, maybe just 1 week ago, a paper, okay, by Stanford or Harvard, I forget. So the title of the Potemkin Understanding Large Language Models. Okay, Potemkin means Potemkin village. Okay, they pretend understand, but in fact doesn't understand. For example, give an example. So you ask the large language model, what is the ABAB rhyming scheme? It seems large language model understand. Okay, the answer is the ABAB scheme alternates rhymes, first and third lines rhyme, second and fourth rhyme. It's correct. But if you give an instruction, fill in the blank here, so that the resultant poem uses the ABAB rhyming scheme, he will give soft. Soft is wrong. Okay, soft is wrong. So it knows its definition, but it cannot execute that following that definition. Okay. Well, then you ask, does alt rhyme with soft? He knows. The answer is no. So he knows the correct answer should be no. That's correct. But in action, it still feels soft here. So it seems large language model in Chinese 一时糊涂一时明白 Okay. That's not. It's I think a deep problem. Another one is illusion of thinking or understanding the strength and limitation of reasoning models with the length of problem complexity. Similar things. So about the reasoning does large language model really reason? Okay, my timer is. So escape. Okay. So in fact, in recent years, so a number of papers in Nature or Science try to review the, large language model in solving some mathematical problem. Okay, so mathematical then I think should be statistics. Okay. So what's the person for us here is we have large language model. We have open source large language. For in Chinese, we have DeepSeek. We have Tianwen. Okay, it's a multimodality large language model. Everything is transparent for us. So every every weight of the edges, everything is transparent. So given input sentence, the activation value of any neuron is transparent. But so everything is transparent, but we don't know its underlying principle. So I think in this targeting at this problem, statistics definitely could play an important role, because statisticians know how to manipulate, from statistical point of view, such a huge data correlations. But for computer scientists, the problem is too hard. Okay, so I think that's we call for the help from statistics. Okay, so thank you. I stop here. Thank you.
Okay, so let's have maybe 2 questions. Yes, go.
So I think the large language model is really a kind of very useful tool. But as you mentioned earlier, a lot of huge system and many inside things is not so clear. On the other hand, statistical models, we have some relatively simple and small model. I think it's kind of at the 2 ends, right? The statistical model is here, simple and transparent and with interpretability. But the large language model is on the other side. Do you think is any possibility that we can something in the middle? So maybe, combine those the both advantage of those 2 sides. We can have some middle-sized model that can enjoy the advantage of both sides.
Yeah, I believe we can find a middle, something in the middle. Okay, so if you look at the large language models, a lot of elements of statistics are involved. For example, so softmax, okay, layer norm, sampling or something like this. A lot of idea, but not the whole general picture. Okay, not the general architecture. Statistics, I think, is deep. Statistics is deep. Deep neural network we are very familiar with, from our point of view, is not deep in idea. Okay, so it's shallow. But the problem now here, deep things, it seems cannot work well. But the shallow things, large language can work. Okay, performance. So I think that's really a need for us to try to combine these 2 together. It's I think it's a opportunity window for research, for both statistics and AI.
哎呀，我也再提个小问题啊，就是我用中文给你提吧，好像懂英文的人，需要说英文的人也不多了，可能只有1个。我就觉得这 large language model 你也提到了哈，它 next token prediction， 我觉得你不管做多好，你哪怕把以前的无穷个句子全记住，你 next token prediction by definition 也不会是真正准确。就像你说的 average 的 answer，average answer 第一它没有 innovation， 第二也不保证正确性，这也 understand 对吧？咱们确实不可能。但是我觉得这一点能不能加上一些这个 statistical measure， 说我这个 prediction 多好多不好什么的，好像这个东西按理说应该不难呀，为什么大家不愿意这么加上这些东西？
现在是这样，就是它最早它就是叫预训练的过程，它就是靠着 natural prediction， 其实让它把一句话先说利索了，把这句话说通顺，但这句话说的肯定有可能就不合适，它都是很通顺，但是它这上下文不行，所以实际上现在的话，它叫做那个 post training 哈，或者叫这个叫做这个。他是说干嘛呢？就说我说这句话，我再说下一句话，在2句话里边我来判断前面这句话说的合适不合适。 你比如说我这个很简单，我可以让这句话我产生10句这个下一句，然后对这10句我进行评估。这个评估其实是有办法的。你比如说我从这句话我要倒回来说前面那句话，看哪个 probability 大，我就可以评估这10个哪个好，这就是强化学习嘛。所以之前的这个算力比较紧张，大家不敢用强化学习。啊，对对对，他在backward过去，然后你10种可能性哪种好，我自我评估，这个现在是可能的。其实那个 DeepSeek 他们做的事儿就类似这种，你包括翻译，我翻译到音，我不行，我从音翻译到汉，我翻译成10种可能性，是吧？到底哪个好的话呢？我再去用这10句汉语，我再回到那个原始的英语，我去算 conditional probability， 我就来评估哪个好，是吧？所以现在实际上是这个在强化学习这块儿，他试图把这个在更大的 context 下把这个打通。那这时候其实统计学就应该就有更多的这个发言权。现在是这样，就搞计算机，我们这帮人吧，统计学训练确实不行，确实小儿科，所以他太深的东西想不出来。你看我们这么多年，我刚讲我那个历史，基本统计学你们研究的方法我来用，我也很难去改，就没这个本事，是吧？我能用好，比如说这个东西到我这个语言的环境下，我怎么用比较合适？它大概这个水平。所以，但这块显然就这里边有很多问题都需要统计学来介入，但是靠传统的统计学又不行，它必须对深度学习这一套东西要比较明白，它才可能找到这个点切入。因为它这个研究确实有难度，因为你像 DeepSeek， 它即使是模型号称不太大，它也是6-7千亿的一个参数的模型，6-7千亿。然后我们这个研究很困惑一个，你做小模型做得很精致，但一到大模型可能就趋同了，就他用一个很笨的方法，他到大模型，你精致的小模型，在小模型做得特别精致，数学特别好的一个东西拿上去，不管用了，所以他还要在一个大的一个大尺度的一个这个上面来做，所以这个其实对统计学员来说也是有挑战的，也是非常有挑战的。但是做和不做，我觉得对统计学的发展可能是意义不一样的。就是再过10年，你不做这件事儿，有可能就别人做了，说不定就会对我们的发展就会有影响啊。因为这个大模型本质上是统计，这个没错。就刚才说那个你说的任总说那句话哈，它这个大模型本质上就是统计，全是概率在里边，是吧？
孙老师，你是如何看？比如说用扩散模型去取代 transformer， 甚至可以改进的扩散模型，比如说扩散模型最后加上那个最优传输，甚至扩散模型加上一些比较好的受限的那个后沿概率采样，这样能够在短短的几步之内就能够采到一个正确的样本做 inference。你们有做过这方面探索吗？
有过哈。我是感觉这样，就是说的像这个包括 network prediction 这种东西哈，它就好像画画，比如说我们画画，它先画个素描，就画一个大概齐的样子，这个还是要靠这个 network prediction。然后这个素描你要把它变成一个很好的那个，你要注重细节，可能用 diffusion model 比较合适，就它补细节，它补细节的时候的话，它有可能不需要那么大的上下文。我只要看 local 的上下文就可以，所以我们的处理是 global 的这个 dependencies， 还是要靠这个类似这个创造方法或者图像中的 CNN 这些东西来捕捉。但是你不一定抓得那么细，不一定一下关注到细节，因为你眉毛胡子一把抓，你最后可能2个都抓不住，是吧？所以先抓主要的，到了细部，我们再用 diffusion model 来做。啊，这时候的话，你也不用看那么远。把它细部做好，所以我们一般是分2步走，就我们这个组是这么看这个问题的啊。
好，因为时间关系，我们就到这儿啊，感谢孙茂森教授。
瑞博呢，请您也上来。对，对，稍微预告一点。
我们还有点时间，那我简单说。
就简单说一说，对，就快，对。就是还有，就请。好，请坐。我就坐旁边嘛，就我吧，对。然后王岩老师，对，请。
看有什么问题是吧？
对，我就有几个问题，挺简单的。
我简单说一下。
对，我们接下来是我们的 panel 环节，对。我是这个环节的主持人杨鹏坤，我们也很高兴在这个环节请到了来自我们有业界有学界的，我们在 AI 啊还有统计这个各个领域有很多成就的一些学者，有芮祥林博士，我们有朱松纯教授，有王楠教授和孙茂松教授。然后我们这场 panel 主要就想讨论一下我们在 AI 时代，我们今天我们这个会议，我们统计与数据科学的一些发展，还有我们的未来的一些展望。对，首先我们今天早晨其实有很多老师都提到了我们统计跟 AI 的一个关系，然后也提到，包括今天早上邓老师说我们有一种观点说 AI 就是统计，当然这个观点我想大家肯定各自有自己的看法。然后，但我觉得现在有一个普遍的一个共识，说 AI 和统计必须要有结合。所以，首先我的第一个问题是说，这种结合大家认为是统计的一种回归呢，还是说我们要对统计学的一种深入的重构，还是说这两个领域要怎么样的一种融合？对，先从孙老师开始。
我来说几句，因为我原来现在有很多种说法，你去问计算机，我们计算机学院的院长说 AI is computer science is AI。因为我给计算机系的人就这么说的，现在甚至化学系的人说 AI is chemistry is AI，and of course the physics Nobel Prize 给 physics 说我们也是 AI is physics，my God，of course AI is physics， for many reasons。当然我们这里就是 AI 是 statistics is AI， 现在打破了这个边界，因为我本人是学 computer science 出身，后来我们在 statistics 当 faculty 啊，在converted 啊，但是同时呢，我也在机器人呢搞航天的系和 psychology、cognitive neuroscience 这些cognitive science 里面任教自动化呀，现在也搞音乐这些东西，所以我觉得它确实一个 fundamental 的 thinking AI 把很多学科都 integrate 进来了。因为 AI 里面有很多哲学问题，我刚才现在谈了，有 psychology、neuroscience， 它要回答这个 AI 的问题，它从很多个层面上来回答它。那么我们作为 statistics people 的话，我们应该积极的参与进去。但是我们有什么强项进来？因为当时Yang Delu 在我们那里，我到UCLA statistics 去的话，当时说做 big data，大家都意识到 machine learning 是 big show。说一个 big party is coming， 那是2002的时候我去教引他们。The party is coming, we get ready 所以我们把桌子都铺好，是吧？大家到我们这里 party。我说 unfortunately，就是他们结果到隔壁邻居家里开 party 去了，没到我们这里来。这个 party 本来应该在 statistics department 来开这个 party 是吧？我们是 host 是吧？我们当时我说 forget about it 可能到隔壁去了。这个隔壁就是 machine learning 的人呢，把这个 idea 给偷过去了。因为 machine， 你看什么叫 machine learning 他们当时 machine 呢，就是 Hinton 他们就讲的叫做 model， 他们的 model 叫 machine， 他们叫做 Hornbox machine、Boltzmann machine， 他不是说 computer 那个 machine 的概念，它就是 model。然后呢，他说，如果你是个 model 吧，大家听不懂。然后呢，这个 regression 大家更听不懂。你说 model regression 就是统计，他更听不懂。他就说干 learning 其实就是 regression， 所以他把这个词儿一下子换了换成 machine learning， 大家全听懂了。然后，对，popular 的 party 到他家去了。但是他后来又提出 deep learning， 你看，后来我当时说 deep learning 是什么意思呢？它其实就是 EM algorithm 里面那个 iteration。其实大家理解成为以为我要 multi-layer 的这个多少层的那个100层是吧？就 deep。其实它 hidden 不是那个意思，它的意思就是说我有 infinity of iteration， 就是从 hidden variable 到那个 bottom 模型那个东西，它就是 EM algorithm 的一个我们现在叫 alternative backpropagation 或者是这个事情。其实就是一个把这个概念就变成一个 deep learning， 那么大家非常的 popular， 他们非常的会 marketing， marketing 这个能力，我觉得statistics人是不具备，不具备这个能力，所以我觉得本来 technically 工具都在我们手上，但是我们缺乏 marketing 的人，最后呢，当然沈老师说了，你最后需要 performance driven， 是吧？因为我们不会 computer science 那一套 big code， 最后。我们 lose 就是被别人偷了这个steal 了 thunder， 我可以认为就是在本来是我们的 party， 那么我是很对打抱不平为 statistical people， 因为他们的很多 idea 什么 stochastic gradients、longevity dynamics 都从我们这里来的，所以那么后面其实怎么能够夺了回来，我估计也夺不回来，因为他们也不 cite 你们，我告诉你他根本就不 cite。因为我们有很多 Monte Carlo 算法呀，和我们的 model， 你看他们做的那个包装模型那东西，都是我们 frame model 那个原来，他根本不 cite， 因为他 control marketing， 有自己的这个媒体在不断的灌输最后认为是他们的东西，那就没办法，这个事情已经大部分人都已经决定了这就是很可悲的事情。
连他们领导都这么认为
对，因为他们。这个你包括沈老师他们读的肯定是读他们的，他肯定不会读你们的，是吧？读我们的算法的东西，因为那个东西它是在理论的东西，它只是用，大家是在用，好不好？这是我的一个观感。
首先我想感谢常老师、刘老师的邀请，非常荣幸参加这次跨学科的圆桌交流。那么作为一个清华的校友，我也为清华统计和数据科学系的迅猛发展感到由衷的高兴。那么我想这个问题呢，应该是所有的统计学家，包括我自己在内，都在近期深度思考的一个问题。我想提一下，就是去年大概3月份、4月份，我们统计界有一个火炉边谈话 Fireside 的 Talk， 这个也是由我们的清华校友郑田老师、林希红老师还有其他的统计学家共同组织的，产生了非常深远的影响。这个 Fireside Talk 呢，就统计在人工智能时代面临的就是研究方向上的一些挑战。以及作为很多核心器官统计核心器官，在这个人工智能时代需要做的一些变革，还有就是在统计的研究生教育上课程上的调整，3个方向做了非常深入的讨论。我想可能在座的很多就是统计的老师和同学都有关注这个。火炉边谈话，就如果还没有看到过的话，那么在网上是可以搜索到相关的视频。那么这个讨论就是有一些从可能是统计是现在的确是有个紧迫感，因为有很多新的问题，就是统计的目前所面临的数据和传统统计所处理的数据有非常不一样的地方。不管是从数据的规模上讲，还是就是数据的类型上讲，那么我们现在就是大数据可以说是在很多的学科，不管是医疗上、金融上已经是无所不在，而且是非常规的数据比如说文本文件、语音文件、图形文件也变得非常的common，这个就给我们带来，我感觉还是有很多的机遇，我们可以做。很多新的问题然后朱老师也刚才讲到，我们统计学家其实是有非常多的工具可以用上去，但是目前还没有用上去，所以我们其实是有很多的机遇，可能过去没有完全的把握住因为我自己在过去几年对强化学习这个领域非常感兴趣，也在学一些新的东西。我感觉要作为统计学家，如果我们想做新问题的话，就必须要学一些新的工具。就是了解一些新的方法这样我们才能够，然后也要更开放的合作，这样才可以做这些新的跟大数据有关的问题那么我在学习 强化就 reinforcement learning 时候呢，就发现其实reinforcement learning 不管是理论的框架还是在算法的设计上，都有应用到很多统计的核心的思想。比如说从理论框架上来讲，它是基于马尔可夫过程这个其实就是概率论上的一个建模。如果是从算法设计上来讲的话呢，就很多统计的核心思想，其实在强化学习的algorithm 当中都有很多应用。比如说 UCB algorithm 是 based on confidence interval 不确定性置信区间的这个概念。其他的包括 importance sampling double robustness 都在强化学习当中就有很多的应用。包括我们今天上午的几个主旨报告，像Win Wong 教授的报告，就是关于贝叶斯推理在深度学习和大语言模型中的应用。然后在王老师的报告中也提到了 quantile implicit network， 这个也是我自己感兴趣的一个方向，因为这个也是我们统计里边就是关于要学不光是 reward 的average。我们要去学习这个关于 reward 的整个的这个随机分布，这个对就是说跟测相关的一些应用，比如说在金融上、医疗上，那么通过这个 distributional learning， 我们可以在高风险的情况下做出更好的预测。所以我自己个人的感觉还是这个目前我们有很多新的题目可以做，然后有很多的机遇。
各位好，我是芮祥林，我是在华为巴黎负责拉格朗日数学研究所。我个人的看法是 ，AI 和统计是一个目前最好的结合，因为统计是目前在各种 AI 算法里面唯一可靠的工具。但是统计也有它天生的 bug， 也就是说它的那个互信息，你是很难去刻画的。举个例子，就好像硼磷硅，你可以组合成P 型半导体或 N 型半导体。硼磷硅本身事实上它里面有自己的一个物理规律，但是它们俩组合在一起就会发生类似相变一样的东西。你很难到目前为止很难去用统计的方法去刻画。事实上，你看我们在学整个随机过程的时候，往往都是贪图方便，假设是高速过程，或是那个或是 IID， 这样的话，你可以利用传统的基于函数、基于微分方程的方式形成一个方程组去求解。假设你能够找到解，你可以找到这个函数，就可以。因为真正的因果关系是函数关系。那当然你通过随机变量去解方程的话，可能找到是随机变量之间的关系。也就是说，你最终还是你只是把问题往后延了，你最终还是没有解决如何去刻画互信息的关系。我觉得这是这整个深度学习以及大型语言模型里面最天然的 bug。然后当然我们现在有很多政治化的方式啊，或透过后验概率采样啊，最大后验概率这些方式去规范它，但还是会发生不可预测的现象。我觉得可能下一步可能是在目前基于贝叶斯类的这类的方法，我们可以引入新几何，以及黎曼几何。新几何的话是利用新结构、新映射以及新算法去从宏观层面方向去描述这整个深度学习算法的它的动力模型啊，这个就比如说它的状态空间、像空间，以及它的那个哈密顿系统。当然，你可以用黎曼几何去描述，比如说是黎曼流行啦、黎曼测度去描述它的一个local 的结构。但我觉得真正要解决的话，可能一个数学的方向，这不敢保证啊，只是说可能，比如说是引入范畴论，以及引入拓扑斯，因为拓扑斯它有丰富的 AI 语义结构，这样的话可以比较从二阶的去阐明如何在零阶方面学出一阶的结构。我觉得这可能是数学方面可以探讨的一些方向。总之，回到 statistics， 因为我本人 也对 statistic 这块非常熟。我觉得这是目前唯一靠谱的工具，但可能要彻底解决，比如说是可解释性问题，以及真正的靠谱的可预测性的话，可能还是要引入一些其他的数学工具。
我是感觉啊，这个统计学和人工智能啊，这两个学科还是最接近的啊。它一个最突出的特点都是 data driven， 都是从这个大数据中来，是吧？这个当然，这个统计学是大数据，人工智能是大数据，是吧？这是还是有差别。这个统计学，试图比如说我去采样，是吧？我整个这个大数据空间说不定处理不好，我去采样，那个人工智能是它不采样，它所有东西都拿来，这还是就既有联系吧，哈，也有区别。但是比如说统计学我是觉得统计学整个它给出结论是靠谱的，这个人工智能给东西让你心里不踏实啊。那这块儿这也是一个感受，但是就说明统计学肯定在某些地方应该能够帮这个人工智能哈，这是第一。第二的话，我刚才讲了，这个人工智能这个大模型系统啊，它那些很奇妙的表现啊，你也可以说奇怪，也可以说逆天，反正这种表现。但也有人说这个东西可能你观察的不对，也可能没这种现象，也可能不像你说这么严重，是吧？但不管怎么样，它那些性质吧，它还是人类构造的所有计算系统从来没有过的现象，就是任何计算系统没有出现过这种现象。那这个东西呢，好在它所有东西都是透明的。所以这个实际上，然后再就是搞人工智能这帮人不是很深刻，对吧？那统计学的深刻的东西有可能切进来，然后它那个整个就是一个透明的数据集，是吧？所以我觉得这个如果就这一路现在大模型的人工智能，我感觉比如在语言模型这个角度啊，这个走的差不多了，就是再什么大招，我觉得可能也出不来，但强化学习还可能有招。就是我不做 next word prediction， 比如我做 next sentence prediction， 我这个还会有招，但总的来说，它整体来看也就这样了，好像不会变出太多花样了哈。那你再往下走，就要解决它的什么 reliability、什么 trustworthy、什么反正这类问题。这类问题的话呢，需要有深刻的这种思辨啊。在这种情况，就是如果统计学能够帮助我们把这个大模型的基底给它搞出来，我就有可能设计更加深刻的小模型。然后这个小模型就会摆脱刚才朱老师讲的那些高性能的，就对那个资源那种消耗，是吧？然后他做的也比较靠谱，那有这种可能。如果这种情况发生了，那统计学对人工智能就是一个直接的质上的一个推动啊。所以这块我觉得是有这种可能性是有的。然后两边，刚才邓科老师也说，两边都往中间靠，肯定会对两边都会产生影响，都可能会产生影响，是吧？这个它不是简单的靠，就是一定是这个各有所失所得，但是肯定最后的结果，因为这是碰到一个全新的东西，肯定结果是好的结果，我觉得啊，对双方的对两边的深刻性和它的这个适应性都会有比较大的这个改观啊。
好，谢谢各位，对，谢谢各位从各种不同的角度都谈了一下我们对 AI 和统计的结合。我们接下来可以一个简短一点问题，就是大家刚才谈论了很多不同方面的强化学习，有语言模型，我们谈1到2个统计理念，在现在的 AI 时代，就觉得仍然是不可或缺的一些统计理念。
我来讲一下这个问题啊，我回应一下申老师说的一些 surprising 的 amazing 的一些 performance 的。我从统计的理解，我不能有一个很严格的理解啊，但是我作为一个学统计干了这么多年的人来考虑这个问题，因为现在很多人把 AI 就是认为是大模型的哈，只不过是这一段时间大模型在 transform。我相信2年之后，也许大家就不谈大模型这个事儿了啊，因为过去你看以前开会都说 support vector machine 对吧？所有的人都 support vector machine， 有一个隔几年就换一个。这个时候 AI 的话，到底什么是 AI？ 所以我回答一下啊，申老师那里面有几个 amazing 的问题。第一个是个 double curve 的问题。以前你看我们统计里面就会有 training set、testing set、validation set、testing set， 是吧？我们有3个结合，我才能把这个模型是一个 OK 的 work。但现在大模型里面就没有这个概念了，因为他们把所有的能够用的数据全放进去了，你就已经没有 validation set 也没有 testing set 了， 就作弊了，就相当于是吧？就是你的所有的题他都见过了，所以说这个时候你要说它的 performance， 就它是不是真的是个 performance， 那个 curve 是这样来的，就是他把所有题都放进去了，它不存在我们原来说的那个概念和 validation test set， 这是第一个为什么它有那个 curve 那么第二个事情呢孙老师说了这个 one shot learning 这个概念这个 one shot learning 看起来好像是说我刚才告诉他怎么说是吧？那个 prompting 那个话怎么说的，突然就会是按照我这个话说了，就听到了，好像觉得这不是 one shot learning 它是什么呢？英年最近写了一些东西，他写了一个machine learning的一些解释，就是其实它没有什么太多的 mystery 在这个地方。那么它的向量的表达，它一个很长的向量呢，其实也有 decomposition， 就是我们的embedding 之后decompose 这个我不能展开说了。然后呢，它也有很多 parsing 的结果。孙老师，它其实里面有 parsing， 它只不过是有很多 redundant 的 parsing 在里面，就是这个 parsing 这个结构然后呢，使得你这个 attention 呢，你刚才说的那句话是吧？它用这个结构把它相关的那些，因为它里面有很多可能的要解那个办法的。所以呢，你刚才说了一个办法以后，他把那个东西跟他相关的那个 pass graph 把它给 prompt 出来了，就是按照这个办法来去联想，所以他又给你一个解。那么第三个问题呢，就是刚才不是说他做一个简单数学题36加上什么52，搞一大堆出来是吧？最后答对了，这是一个谜因为到底怎么答对的，他乱七八糟的，最后还碰着了是吧？最后歪打正着了，就是这是里面一个 fundamental 的问题，就是说他那个 token prediction 这个事儿，其实他那个解是不 not identifiable， 数学上讲是吧？这是不 identifiable， 你有可能有好多种办法把它给解了，就相当于我们，比如说我们正常的是应该拿筷子这样拿是吧？去捡那个肉丸子是吧？吃了，只要你把肉吃到嘴了，这个任务就完成了是吧？但是你那个有的人不会捏筷子，那筷子捏得很难看，但是他把东西搞到嘴了。那就过一个了，所以说他这么捏筷子还这么捏筷子，他就有好多种解，是吧？所以他最后还能够把你给答回来。所以呢，这个是个 fundamental 的。那好，那其实就是说这个问题是 not well defined。那么它 define 的东西你 not identifiable 以后，那就是要有更多的 regulation 来解它你的 regulation 在哪呢？就是你要去完整的听到一个 totally new situation 的情况下，它怎么解？所以这就是 value 最能够泛化的是 value， 所以这是所谓王阳明的什么龙藏悟道，就是这么简单。就是在一个 total new situation 的情况下，你最能够 generalize 的东西是什么？就是你的 value， 就圣人之道那么这个时候呢，你的 valuation 那个东西能够去回答这个问题。所以正是因为我们没有这些 value， 它就乱七八糟的东西都可以出来就是各种解都在。这是我对他的这个问题的一个回答。还有一个问题，我刚才想到了，还有一个问题next token prediction 这个事儿，就是你看我们那个通他在研究的时候，你也可以认为 token prediction 就是我们每个人他是有很多行为，所以为什么你看大语言它解决的比较好，但是它在视觉在机器人这边它现在还没法解，因为那个空间比如说这个桌子是啥东西它就很难去 embedding 到这个 token embedding 到一个 embedding space。你看这视觉它就还是没法解，机器人的操作它还是没法解，它现在解不了所以这些问题它为什么说我们具身智能呢？现在还不行那个空间和这个语言的空间又是完全不一样的东西所以我先说到这里我就是主要是跟孙老师那句有些我回应一下。
我注意到有一个统计的理念出现在朱老师的 talk， 也出现在孙老师的 talk， 所以我想这个统计的理念一定是非常重要的。这个理念可能大家也注意到，就是因果推断。那么在朱老师的 talk slide 当中，有一张是关于人工智能推理没有展开讲 alpha proof。那么 alpha proof 和 alpha geometry 2， 大家可能知道，就是去年被用在做数学推理，就包括用来解奥赛题那么30多道奥赛题，现在就是说这两个系统相结合，已经可以解出20多道，已经可以达到至少是奥赛银牌的水平那么我想就是在具身智能，就是朱老师讲目前是已经有5岁，彤彤已经有5岁的 智商。那么下一步的话，如果具身智能要发展出这种推理的能力，因果推断应该是会起到一个非常核心的作用。那这个也是我们就是统计里边非常擅长的，就是我们有很多的，就是已经有很多的理论基础，也是未来可能会在和人工智能相关领域有可能是引爆的更多的一个方向。
我是建议统计方面要结合更多的数学工具，因为事实上我们无时无刻的都在面对一个生成过程啊。我们的语音语义系统，图像不必说，我们整个语音语义识别系统就是一个生成的过程。那生成过程，俗话说就是脑补。那你脑补纯粹只是依赖统计这个数学工具，我个人认为是不够的。可能要引入一些几何与拓扑的概念，比如说几何的不变性、等变性、对称性，这些都可以大量的去简化整个深度模型。比如说拓扑不变量，假设我们真的能够在 meta level 这几个超参之间找到它的拓扑不变性，这对于我们如何去控制底层的真正几万亿个参数组成的大型语言系统，我觉得是有帮助。我个人认为可能要思考引入更多的数学工具，就我刚讲的，比如说新几何啦、黎曼几何啦，然后是那个几何里面的一些特性、拓扑的一些特性，甚至再到范畴论，利用范畴论结合三种经典的算法结构嘛，就是符号、连接跟行动。对吧？行动就是那个 agent， 还有那个 RL， 我觉得可能然后再进一步到利用拓扑式，我觉得这将是一条漫长的路。但是我觉得目前靠大量的训练以及打补丁的方式，纯粹靠统计的方式去搞定生成的问题，我觉得我们永远无法解决这个整个互信息里面的不确定性的问题。
对，我稍微呼应一下这个朱老师刚才讲的哈，确实这个里边有很多不确定性，我们搞不清楚哈。但是呢，你比如做这个数学题啊、物理题解题啊，其实它也分，比如这些题训练的时候不能用啊，它也分，他也试图在这语料里边把这些题给抠掉，就是他们也做了这个工作，就让他保证是这个独立的去弄，当然也可能抠不干净，是吧？它那个效果就是，如果不做这个，好比强化学习，它可能去解数学题就是好比20-30分，做了这个它能达到60-70分、70-80分，确实有一个很大的一个提升，说明这些策略呢还是有效的，是吧？它肯定是把里边某些东西打通，就是没有那个 vector， 我的判断肯定不行。有了 vector 之后，咱们东绕西绕，条条大路通罗马，它说怎么就绕上去了哈？但关键它是怎么绕着，它绕上去那个路径。我觉得就可以研究，它是一个最短路径还是一个什么路径？那个路径是不是关键路径，是吧？就有可能去研究啊。这个所以这块的话呢，其实它这些现象还是值得这个去深入的探讨。有些可能是虚假的，也可能它就朱老师讲的，它可能它本身那个实验设置条件有问题，可能是不对的。但我感觉大概企业这个道理好像还是有这种现象，因为我自己试过它，是吧？试过它，所以这块我觉得还是值得这个探索哈。然后你刚才那个问题就统计啊，就是说，其实我们能感觉到这个深度学这个大模型里边有些深刻东西，其实都是统计来的。确实刚才朱老师讲那是对，我很多我们这个概念，我今天听这个咱们院士讲哈，这是统计学的核心概念。我都以为是机器学习的，对吧？这些我学这些概念全从机器学习那儿拿来的，就他们确实没有再进一步到统计学，这确实是所有那些概念是吧？什么 regularization， 什么 loss， 这种我都觉得是机器学习搞出来的。但今天一听咱们院士讲这是统计学的哈，所以确实有这个，但是确实这个你像它这里边有深刻东西啊，真是要统计学。你比如说那个 diffusion model， 它是用那个 normal distribution 一步一步去做。可是搞计算机的人他根本想不到这条，不可能想到。那我当时就想，为什么一定是 normal distribution， 能没有别的 distribution？ 那我去推导这个能力就没有。那统计那个东西多了，为什么就一定是 normal distribution 去做，不是别的？ 那这块训练的就没有。那搞个统计学的老师肯定，我搞10种常见的这个东西，哪种他的心里知道，他至少可以去试。哦，这个东西不一定非是 normal distribution 是吧？我说问你别的 distribution 针对这个问题可能更有效，那我们就没这个能力。所以这块其实深刻的东西，包括那个 sampling， 在那个干里边的那种 sampling 这个概念，计算机这我们基本上没学到这个概念，就他那个很巧，就是把一些很绕不过去的问题他给绕过去了哈。就这些深刻东西其实都统计学来的哈，都统计。所以这块我觉得。这个如果咱们统计学家深入到这个模型里边，深入到它的那个主要的细节，不是那个琐碎的细节，肯定会提出很多深刻的这个东西啊。你再有一个，比如邓肯老师，我们这些年合作，他做了一个工作就很好，就是做那个 top words， 就是分词那个东西，他在那个 Peanuts 上发表过论文哈，那个工作非常好。但你知道大模型它现在怎么做这个东西啊？这能把我气死的哈。它就是这俩东西，它到 byte， 它不是一个汉字2个 byte， 它甚至到1个 byte， 然后它就这2个共线频度高就捆起来，所以在它的词表里边，它会把什么捆成一个词啊？的一个是，它是一个词。我是读过语言学书的，我怎么看这个的一个是就别扭。然后我就跟他们做大模型的人，为什么你把这个东西你不能去切词，把这个的一个是，它都跨了不同的 constitute 了，是吧？的一个是不是我的一个是什么？不是把这个东西捆起来，他们不管的。但是用邓科老师这个办法去做，他还未必就好。这玩意儿真奇怪，就是，但这个是不是这个问题？搞计算机人，我跟很多人去说这个问题，你们应该做一做，没人做。他说大家都这么干，我就这么干，的一个是就一个是。一看什么 ChatGPT 不是这个，包括那个 ChatGPT 也这么干，就是它完全是机械式的啊。但这个问题，如果邓科老师介入，真是深入研究一下的，我是相信，把它做合适的处理，就的和一个应该啊。
这个问题的话，就是影响，就是整个我们那个 career 里面一个 puzzle 和我们的所有的学生的一个最大的 puzzle，就是你拿一个数据集来了是吧？只要你把那个任务定义清楚了，就是 next token prediction，你就 end-to-end training 端对端训练，你任何可解释的美妙的数学模型根本捞不到什么好处的。一定是输，所以呢，你说的这个是的这个问题哈，其实就是说它缺乏 regulation 的一个很重要的表现，因为它对于这个 next token prediction 来说，这个就也许就是最优解了。那么它之所以产生这个问题呢，就是说你要有很多其他的 value function 或者是任务来 regulate 它的时候，才能说，因为你要说我的是吧？这个什么是那 ownership， 还有这个什么东西，那些东西呢是。在这个 next token prediction 之外的东西了，所以这是为什么我和我们因为这个大数据这个事儿是我们搞 computer vision 的人搞出来的嘛，从连王山搞出来的，李飞飞他们。后来我跟他们一个组 Muri， 我就天天骂他们，跟他们说你们这么搞下去是吧？就相当于爬树是吧？因为爬树你想登月，你爬树每个 task 你是一个树是吧？爬这个是爬了一个树，那最后还是没法登月，那就是我们要有无穷的任务。所以呢，最后这个 data set 这个任务的定义是谁来定义的？你看到没有？比如说我们就是做一个 prediction 这个任务的话，那你就只能 end-to-end training， 你不可能，你像我们想搞个数学模型去占任何便宜都占不到，啊，你的 performance 一定比它差，所以你的 paper 就没法发表，啊，这是一个确定的。所以这就是大数据小任务，你就有一个任务，单对单训练。他说朱老师你有本事你就别跟我说虚的，你就来一个他妈模型跟我比，你就在比。是吧？你别跟我说别的，这就是，但我说不过他，因为他就是 performance 绝本的，对吧 ？end-to-end training， 那你要，但是最后我们说好，我们要比这个事情，最后你要说把我们引到正道上去，这是为什么？后来我们就觉得，啊，我们搞数学的人、搞统计的人肯定是比不过他的，啊，这 accept， 啊，那么怎么办呢？就是说你们到底搞清楚，到底我们要干多少任务？是吧？你把那个事情说清楚了以后，你就发现他有问题了。他干了这个任务，干不了那个任务，是吧？所以我们当时 review 的人就是两派哈，就是理性的人，就是我们的 paper 当时，如果我们的 paper 送到一个这个搞大数据的这个测试 deep learning 的人手上，他就说你就他妈别跟我说别的，所有公司我都不要看。就这一个任务。对，你就给我这个任务在 data set 你给我试一下，啊，你试不好你就别跟我发表过来了，我不看。这就是他们的就是经验主义的办法，是吧？我不要看数据，啊，就看
生物信息。
就是这表。好，但是这个 paper 如果送到了那个理论派的手上的话，他的回答也很精妙啊。他说你这个 data set， 你这个算法仅仅是 only working on these tasks on that data set。There's nothing you can talk, conclusion about what your contribution really is 啊，你就是在这个 data set 在这个任务上搞了最好一个表是吧？这是 ad hoc 啊 ，make no contribution to the understanding of intelligence， 拒绝啊，就是 reject 啊，所以两边就是这种打法。最后的话，最后打了以后就是看哪边的人多。最后就是一个 rejection， 就是温旺说的那个事情，就是你把 paper 送到哪个 pool 里面去 review， 结果那个 pool 的人越来越多，他钱多人多，最后他们就占领了，其实就是这么一个 ecosystem 的问题。那么我要回答就是你别让他去搞什么统计，能够去证明他们那个东西，证明不了的。那么所以我就觉得统计和 AI 的一个关系其实就是 mathematics 和 physics 的关系。physics 呢，它是个 domain。它有很多问题，是吧？那么 mathematics 是个工具，是吧？数学物理像邱振彤他们就是个 tool， 但是你的 tool 的话，那在我们这个 domain 里面 ，statistics 就是个 tool， 是吧？那么它的 domain 是啥呢？是 neuroscience、psychology、哲学、文学这些东西。因为他们的问题是个什么问题？你到底要解一个 intelligence 是个什么问题？我们并不是个 least token prediction 的问题，我们是要创造一个什么样的系统？那个问题是个什么问题？这个问题没说清楚。那你们创造出来的这种系统当然可以有用，但是它不是一个 fundamental 的towards understanding this whole thing 这是一个根本。但是或者为什么我坚决没有回头因为我们那个时候搞大数据连环山都是我们搞起来的，或者我到2010年的时候，我们坚决没有回头，虽然特别的热闹，特别的这么 citation 很多，但是我坚决没有回头去搞那些东西。我们走的这条路，就是今天我给你们讲的这个事儿，就是。The ultimate goal of intelligence 是什么？build 一个 person 这是什么意思？所以呢，我们要 statistics 的人呢，要 learn 很多从 psychology、neuroscience 和 humanity 这里面去，它是 domain。这个问题是个什么问题？是他们定义的，我们只是个工具好不好？这是为什么英联我们后来学了很多，就我从里面跳出来了来研究这些问题
好，谢谢各位呢。我们也快到中午吃午饭的时间了，所以最后也是顺着刚才朱老师提的我们这一个 AI 的终极目标，就是我们现在最后一个就是想让大家可以展望一下我们现在 AI 可能对于各个领域的影响，比如说我们对于学校搞教育，还有我自己可能是做 theory 为主的这些。做理论的怎么在融入这些实践和工业，还有这些 AI 对社会、对伦理各方面的影响，大家可以简单谈一下自己的看法。
我们现在的问题，我写了2本书，为机器立心，为人文复理这里面讲了很多事儿，就是对 AI 要影响 society 的影响我们的 civilization 还有 culture， 这里面就到了那个high level 上去了，就是。social scale 的 AI 就是我们的定义的 meaning 是什么这些问题其实一直是 science 回答不了的问题science 说我给你一个问题我去解，但是他没有定义一个问题是什么，所以我当时说了一个东西比较 offensive 的，因为我经常说话比较 offensive 就是我们中国人会解题，比如说我们证明一个猜想是吧，解了一个东西都是这么证的包括邱老师真的是证明一个猜想，我说那是很大的本事。但是那还不是最好的本事，最好的本事你定义一个问题，对你提一个猜想，你定义一个问题，定义一个 framework， 是吧？开创一个学派就是定义一个 framework。所以我觉得在这个过程之中，我们中国有机会来定义什么是 AI 什么是要做什么样的 AI， 那这决定于我说为机器立心也好，为中国思想也好将来对整个 society 的影响是什么？这就是我们要什么样的 AI。是吧？你怎么去保证它对人有用，还是跟人没用？这些事情，这都是人文社科的问题了我就不展开说了。所以为什么我在北大的时间待的比较长？因为那边的人跟我交流的人文社科的东西多一点因为我不爱跟社里的人交流，我跟人文社科人交流，因为问题都在他们手上到底我们要什么样的一个？到底想 build 一个什么东西，是吧？这是一个 domain 的问题 至于用什么工具那是再说，是吧？我用是要锤子还是要扳手，是吧？但是先把这个问题搞清楚啊，这是我觉得让大家特别是年轻的学生要想这个问题。我们往往读 PhD 的时候，就老师给我个问题，我觉得或者是很多人都在做这个问题，哎，我要去做一下。我读了一个 paper， 觉得这个地方我可以 improve 一下，但是做了以后，这个东西很快就 maybe irrelevant 啊。好。
就我自己的经历，因为我是之前10几年一直在传统的统计系，从过去的6年是在一个交叉学科管理科学系，所以在过去的几年里，我觉得是目睹了就是刚才谈到的这个和人工智能的融合，不光是发生在统计里边，也是其实同时发生在很多其他的学科里边，比如说我的同事里边有做 operation research 的，然后他们的领域也是受到很大的就是 AI 的影响，他们也开始做一些非常大规模数据 optimization 的问题及 stochastic optimization 的问题，就是考虑不确定性。那么在其他的系里边，比如说 marketing department，他们现在是完全变得是数据的 driven，就是 completely become a digital marketing。在 accounting department 里边，他们也是现在完全开始转向用大语言模型来处理像税收的文件，就有很多的因为我们统计，我想是 data driven 的，所以我们可能要。就是说，如果想找有兴趣的切入点的话，可以通过和其他学科专家交流的方式来找到他们关注的问题，然后我们有什么样的统计的工具可以应用上来解决一些在实际当中比较重要的问题。因为我想在这个融合的过程中，我们也需要找到自己的独特的地方，就是我们的自己的 identity 需要有辨识度。我们当然是有非常多的工具，比如说像因果推断、像不确定性刻画，以及其他很多重要的问题，像对 AI 算法。比如说是 trustworthiness 隐私保护、公平性、伦理性这方面，其实都有很多统计的工具可以用。那么我也顺便说一下，就是 AOS 每2年就是有在 GSM 北美最大的统计会议上有一个 invited session。Alan 买闷和我在我们就去年退任之前 organize 了一个 session， 是今年8月份在田纳西州。在这个session里边，我们有AE 和 referee 推荐3到4篇文章。那么在今年夏天的4篇文章，所有的文章都是和大数据以及人工智能相关的，其中包括苏伟杰老师的一篇，用 hypothesis testing framework 来 address 在大语言模型就是 watermark 的重要的工作。那我想就是这个融合就已经在发生，我们可以就是抓住这个机遇，然后统计是非常有可能对就是具身智能未来的发展做出非常核心的贡献。因为我想未来的人工智能就像彤彤的未来现在是在6岁的阶段，但是它未来应该是可以有这个因果理解能力，能够像一个科学家一样严谨的推进，也能像一个工程师一样能够高效的学习，所以在这个过程中，我想统计应该是有很多的机遇可以做很多重要的工作。好，谢谢。
我是希望AI 的发展未来能够把3种结合在一起，也就是说符号、连接跟那个行动。因为各有各的好处，我在这就不展开了。但我们可能需要从数学上找到一个统一的架构，能够把它们无缝的衔接起来。然后在这种基础之上，我是希望能够解决因果关系，因为我们现在人类习惯的方式还是用一个普通的变量去建立方程，不论是微分方程、偏微方程或其他的。积分方程，然后去找到它的解，这是我们所习惯的一个物理的世界。那当然，我们在目前基于统计的话，只能用随机变量去建模了。这里面有一堆的好处，有一堆的坏处。所以说，我是希望未来我们能够找到一个方法，能够去把它统一起来，然后能够 更彻底的解决比如说因果关系的问题那以及可解释性的问题。
我觉得这个未来2年啊，这个人工智能哈，当然不仅仅是人工智能哈，加上统计学加上统计学，这个肯定在 AI for Science 上能发挥很大的作用。这几年我觉得应该对这个各个科学领域都去扫视一遍看看有没有我叫根问题 root problem 然后有没有配套的大数据。如果有的话呢，这个问题比较重要，用人工智能的办法加上统计学办法，肯定可以把它解决的比较好科学问题比那个自然科学问题比社会科学和人文要容易。我呢是把这个自然科学问题定义成困难问题中的比较容易的，社会和人文是困难问题中比较困难的因为比如自然科学它都是在分子层面的，分子这个层次它是比较稳定的，它的性质是吧？而且中国有句老话叫天行有常，不为尧存，不为桀亡，它就是在那儿客观的东西，它一头稳住了，别的事儿就好办。再有文本文献是吧？但光靠大模型也就必须有大模型，但光靠大模型也不一定够。统计学这时候它为了让这个结论更好是吧？统计学在里面也发挥作用。我觉得这个东西应该这2年赶快做赶这个大把的机会，做晚了就没了。这个刚开始这头一茬桃子是比较好摘的，摘晚了就被别人摘光了，你要往高了摘就费劲了。所以这块其实我在2020年在学校里面就讲这个事儿，就当时已经看很清楚，就应该赶快做。现在有点晚，但还不算太晚，还来得及这是第一。第二，在人工智能领域，其实朱老师讲的，我觉得我们这块还是有很多探索空间。你比如刚才讲，为什么语言模型它基本管用？语言模型我是琢磨这个问题，因为语言那个词 word 或 sub word 它的边界是清楚的，它的语义指向也基本清楚，就是虽然它有多义词，但基本上都是稳定的。所以它自己有稳定了之后，然后它上下文的这个作用就相对简单一点，它就容易做，是吧？所以 network prediction 它就 work。到了图像，我觉得就不一样了。到了图像，你弄个什么3×3的一个 patch 或者9×9的一个 patch， 它首先它那个东西它不是一个独立的东西，不像词边界是清楚的，是吧？然后它那个语义指向就更加灵活，那语义指向你不知道它是指啥。所以它的语义要完全靠上下文来确定，基本上要靠上下文，上下文又是2维的，那变化又大，它那个变化空间比文本空间那1维的那个大了，不知道，我觉得是一个数量级可能都不止。所以这招用到图像里边，要彻底解决图像问题，它就难，是吧？但是它现在确实又做出这个效果，就说的，你比如说现在图声文，你看它基本上还靠谱。就随便拍个照片，让他用文字来描述，大概90%是靠谱的，能做到。这就解决个什么问题呢？就是说他不去看那个细节，他没去抽那个特征，包括什么边呀、什么就是部件他有了整体感觉了。就刚才朱老师讲了，他好像有了这个，他从 bottom up 他上去了，是吧？他有了那个 top 的那个感觉，这个感觉是以前从来没有的。就是以前图像，就说我不分析那 component， 我要得到整个这个picture 的这个东西给它说出来，这不可能的。哎，现在它这个能力有9层了，缺什么呢？反过来，我有了这个 top 这个东西有了之后，我能不能再去做这个好比 object 什么 detection 什么这些东西，把它2个都打通，是吧？那这块的话，我觉得现在图像模型还是没把这个打通，所以这块从人工智能研究角度，这个还是有很多事可以研究。那你要到了3维空间，这个事儿就更复杂了，是吧？所以人工智能这块本身，我觉得也是有很大的发展前景
好，非常感谢4位嘉宾。我们今天也就是讨论了很多关于 AI、关于统计、数据科学的方方面面，然后最后我们也谈到了好多 AI 对未来社会的可能的发展。我们今天的 panel 就到这里结束。最后再次感谢4位嘉宾。
好，5位老师合张影。
OK。
华大学数经济学政策的杨颖，今天非常荣幸的邀请到哥伦比亚大学统计系政学教授这个教授是统计方法研究学领域的毕生学者，开创生物到气候科学等复杂数据的模式发掘方法，其杰出成果荣获 ASA 杰出应用奖、ISBA 米切尔奖，并当选 ASA 然后 IMS Triple AS 的 Fellow。他还因卓越的教学与行政能力获得哥伦比亚大学的最高教学奖。他今天给我们带来的题目是Distribution Informed Learning by Kernelized Stain Discrepancy Calibration。好，下面我们以热烈的掌声欢迎郑教授。好，请。
君还有宋经邀请我，还有科邀请我来参加这个 1 year anniversary celebration of the department。我这个 talk 我很少用中文给 talk， 所以 even if I want to use Chinese， 我也不可能 use 100% Chinese， 所以可能 most of the talk 是用英文来讲。我这次这个 talk 其实想要讲的不光是一个我们新做的一个方法，而且也是要给我们一个 center 的 research 做一些宣传。因为我们在吃午饭的时候，还有我前面开会交流的时候，大家都会说，有些时候想做一些 machine learning 大的问题，但是数据不太好找。那我今天就会花一点时间告诉大家一些咱们统计学家可以去深度研究的一些数据。我现在是一个刚才那个杨老师介绍的时候，我们那个 title 还写的是 Chair of Statistics， 然后但是 as of yesterday 我是已经 officially 下任了，所以但是我现在还担任的一个职务是我们在Columbia 有一个National Science Foundation funded 的中心，叫做 Learning the Earth with AI and Physics， 其实就是希望用 AI 的方法，然后去改善the climate projection produced by climate system models。然后，所以我们它其实里面很大一部分就是说，希望能够 harness the data 来那个 revolutionary climate projection。然后，这个 climate projection 其实跟我的本科是 apply mathematics. So when I first started collaborating with climate scientists, I find like all of a sudden all the favorite subject of differential equations, optimization, programming all come back because climate system model use a lot of like simulation. It's actually rather organized. If you want to do large language model or computer vision, sometimes you often talk about unstructured data, and you need to actually create artificial structure in order to apply traditional statistical methods. The good news is with climate system model, everything is structured nearly perfectly. You don't have missing data problem if you're dealing with climate system structure because you have full coverage of the Earth. You even do vertical, and you have a lot of complexity, a lot of process in the model. And the conventional method is just like when you're in undergraduate, you learn about numerical methods for mathematical modeling. For example, you do a lot of long chain simulation, try to mimic the real dynamic. But that, if you think about, you have differential equation, and you do long chain simulation, and then that's one end. On the other end, you have the real observational data. The biggest problem with that is that the data is simulation, right? So when you have the real observation and your system model does not agree with it, and it's very hard for you to inverse the numerical simulation of the model to say which part of the model need to be updated to reflect the reality. So that is an open challenge. And also the model, the uncertainty quantification, and also the metrics, right? So this, the first data set I want to mention is called Keogh's Bench. You can write down this word. The Chaos Bench is trying to create a large data set that shows what the physics model does, what a data-driven data does. So they create a big collection of high-dimensional data to see how you can use that to train machine learning, purely machine learning model to do projection. So if you're working on deep learning, computer vision, you want to do a non-stationary model, and you want to say, how can I do ensemble model to improve predictions, this is your data set. So, so to think about how we can use machine learning to improve climate projection, one has to understand what is the current state of the art. So the dynamic system in Clemens's model can often be written as dy dt equal to a r of the current state and then u of the current state. So the r is often known as the resolved part of the dynamic, which means that you can capture that in the grid. The U represents something called unresolved. That is something you cannot capture on that. So in order for this physics to be fully captured, you know the equation have two parts. The part you can model, the part you cannot model, plus some noises. So the conventional approach, when this is sometimes called the engineering mindset, like a statistician usually don't have that mindset, is that if you look at this, U is not captured, that equation is wrong, it's not usable. But in the engineering mindset is that U is not usable, we just ignore it. And we just need to project forward to make things work. By the end of the day, they need to have climate projection. So the current state is that they will take what is resolved, R, and then some other potential, they think some other forcing that may be useful, and then just project forward. So you can understand that this model accumulate biases. The longer you run, the more bias it becomes, and then eventually is not very reliable. And then that's why that the machine learning problem is, we know that the R is usable, and then there is some sub-process we want to do, so can we replace that using a data-driven approach to fit a machine learning model for that? So, so therefore that the workflow of introducing machine learning into climate projection follow a typical machine learning workflow. So you take the scientific problem, you find the training data, the objective function, the model space, you find the algorithm, you design the experiments, and then you will create a model, and then you have the further use of it. So in Clemens's model, some of the most important thing is the objective function is how do you evaluate, and then also important is how do you integrate. So if you use computer vision to classify whether an image is a deep fake or is a real image, and your job is done when the machine learning model is fitted, and you just use it. But in Clemens's model, often when you create a machine learning algorithm, you is only part of the bigger thing, and you actually need to plug in. It's similar to if you study like digital health, intervention study, like business. You also worry about once you have the machine learning algorithm trained, how it perform in an online setting. It could be very different from what you perform in the offline training setting. So this is a big problem in climate projection, a unique feature. So the current way is that the low-hanging fruit, early this morning we talked about like, we should try to do AI for science. There's still opportunity to have low-hanging fruits. The low-hanging fruit here is that you can replace the hard-to-solve PDE solvers with machine learning. You can identify reduced model. Here you actually have a lot of applied mathematics theory guarantee that such space exists even for some nonlinear equations. And then the biggest problem is that the scientists there worry about the pure machine learning method. They don't want the climate projection model to be purely machine learning, just like the next frame generation of video games or something. So they worry about how do we put physics into ML. So here in this diagram, everywhere you see a green is where the physics is being introduced, like how you train, how you create data, how you choose the model, how you constrain the model, and how you train and how you evaluate, all concerns about whether the model you generate is physically consistent. And then currently there's there are a lot of research on how can one use Gen AI and diffusion models for downscaling, which concerns that if you project climate for 10 years, which is on a grid, that grid covers, say, Beijing, a city, but you want to understand when the climate projection concerns the future climate in city, what does it mean for local risks, such as flooding, extreme heat, or the joint risk of this thing. Those things will not be able to project it by the climate model. So you need to take a two-step, which is climate, and then downscaling, which is about identify the fine details of the projection. So here in this talk, I want to touch some of the easiest one, which is how do you use machine learning to create surrogate model? The surrogate model, if you remember, this is the same thing as, let me just quickly go back to the bigger thing. So this here is that you have the grid, and then inside the grid, you will do the processes. So what happens is that you will use numerical forward modeling to project the process one step forward, but afterwards, because it's entire system, so you need to do energy conservation balancing, so that's called a dynamic. So a surrogate model works is that if you have equations here, and you have the PDE solved, you actually know the knowledge perfectly, but it's super hard to compute, very computationally expensive, then the surrogate model says, let's run this model many times, have the input-output pairs, and then replace the resolved PDEs using a machine learning-based model, that's called surrogate, and you train it offline using mean square error, and then you plug in and then to see how it performs. So that's the simplest way, and then there are a lot of such. So this is the second data set I want to introduce to this audience is when sometimes people design such models and they want to make sure, remember I said integration is super important, right? To ensure that whatever you do here can be plugged back in. The most important thing is that you need to unplug here, make sure the plug are the same for the machine learning. So they need to isolate the input and output from the system to be identical for the machine learning as for the numerical solver. So when the machine learning is fully trained, it can just plug back in like an artificial heart and then be able to propel the model forward. So this is one such effort. It's actually harder than we thought, like at least it's harder than I thought it would be. So it took a lot of effort. And also the center produced a large data set that is in a live running model. And then here you have 124, actually possibly 617 input, that's the X variable. The Y variable is, here you're showing 120, but it can be as high as 340. So if you have a method that is to a scalar to scalar regression, and in high dimensional, you will find yourself a 5.7 billion pairs of one of the largest ever benchmarking data set for multidimensional regression, and which non-stationarity, zero inflation, all the issues that you can deal with and have spatial dependence within. So this is a training set for such a surrogate model. And then another way is a slightly different, is called machine learning assisted closure. This is just say that I have the physics and I also worry about some unresolved part. So I'm trying to learn the unresolved part. I don't want to throw out the physics. I actually want to keep this one, but I know this one is not perfect. So therefore, I will simulate the missing part using a higher resolution data, even more expensive. So the training data is very expensive to derive, but the goal is say, let me spend this one-time investment in time to generate this unobserved subgrid and to have the input-output train it perfectly offline and then plug it back in. So I preserve the resolved physics. I like my equations, I will keep it. but then I use machine learning to close the physics for this equation so that it will run more stably. So this is also called, this is here the metrics is more important rather than stability. You also want to see whether this added ML parameter improves the online performance, which is often different from what we have for the offline. So, so after hanging out with climate scientists for a long time, I was looking at this. Initially, I thought this was like, even though it's higher dimensional, it's not a different problem. Then I found something really interesting is machine learning focus on learning short term, right? Is a regression. So from X to Y, well, and then the local functional relation. But the short-term prediction accuracy does not necessarily tell you the long-term behavior of a dynamical system. So one thing we know dynamical system is some of them can be chaotic, meaning that the trajectory is not predictable, that a little bit perturbation of the trajectory at one point, the butterfly effect, then you will end up in another part of the stationary distribution. On the other hand, that we keep saying that the chaotic system have a attractor, which is just a way of saying is a marginal probability distribution of the state in the long term. So that's called attractor. So therefore that I read this very interesting paper saying that they were doing this surrogate training, so they employ different models, and then some models lose the trajectory very quickly. They cannot predict accurately. But somehow they still be able to reconstruct a stationary distribution, so they were able to reproduce the distribution. So that makes me, as a statistician, my first intuition is that these two things must draw on different information, slightly different information. They're not exactly the same. You can predict relatively accurately 90% for the next step, then you lose the trajectory, but somehow you still capture the long-term behavior. So therefore that there is a lot of interest of improving the long-term global scale performance of such surrogate models, and then you can if you are interested in that, you can actually run a lot of time, do long runs using the distribution as your target and fit that directly. But that is very expensive to generate training data. So therefore, the alternative, a very commonly used alternative is that hybrid loss. So in the loss function, let's fit a machine learning model with mean square error plus a distribution loss, any distribution loss. But the assumption, so I actually saw the assumption made by such a hybrid loss is that the goal is still in training the propagation of the function accurately. But what if is not the main function, the mean effect that responsible for the long-term behavior? So this is where we generated a toy example, which I call this a dynamical system with a shifted feedbacks. Is that is a simple linear system that the yt plus 1 equal to a linear matrix times yt plus some error terms, and here we just assume we assume that this system is highly unstable with eigenvalue close to 1. And we create a training data and test it using a little bit different is that they have a little bit difference in the feedback, the epsilon every time. So we generate a lot of training sets, so meaning that we can capture A very accurately, meaning that we can almost fit it without error. But because we're not capturing the error performance of the system, when we employ it online, we cannot get the result correctly. The interesting thing is that this is the observed Y and this is the predicted Y. You can see there is definitely a strong association, but there is a deviation in terms of a systematic bias from Y to Y hat, and then this is how to capture that one. The blue is the raw, and then where the orange color is the true distribution, and then the light yellow color is what we managed to calibrate using our method. So our problem setup is that you do have a data set. The data set is a typical machine learning data set. It's a training, input, output. You have machine learning model. So here in this case, we just say we use a machine learning model that is flexible enough to capture the relation between X and Y. And then you have the new input. Then we assume we actually have one piece of additional information that is marginal knowledge probability distribution. So this is something like we want to project the future weather of Beijing. And then we are using some machine learning model to do the prediction. So in addition to the prediction, we have knowledge about the marginal distribution of the relative temperature distribution in the winter in Beijing. So we're going to use that as additional knowledge. And then so here, we propose to take the piecewise model, and we are not innovating here, but we here say, how do you use knowledge distribution to calibrate? And then here, the calibration is using distribution. Here, we consider use kernelized stain discrepancy, which is motivated by the stain discrepancy as a measure of distance. And our choice of this is not like other than other distribution measure is because of this recent adaptation to use statistics, which allow one to no need to work with two distribution functions. Rather, you have one knowledge distribution and one sample draw from a distribution, then you are able to use this in an analytical form. And then because of that, and also it's actually connected with other distribution measures such as MMD and Fisher divergence, so KL divergence in special form. So it's capturing the right information. Because of the form that you use observational sample from one distribution compared to another knowledge distribution, we were able to use the gradient by taking derivative of the score against the observed point so that we can actually calibrate the individual predictive of the discrepancy of against y hat and do an update. And this, the form of this looked really familiar, so sure enough, we were able to show that if you use a very simplified setting where you say that you are observing a noise version of a truth, ground truth, and the noise is independent from the ground truth, which could be true when you're doing machine learning, because overfitting or biased error can be viewed as errors that is not part of the signal. So we're assuming that you have y hat, which is a noise version of y, and we can show that there exists a lambda that we can apply, a common lambda applied to calibrate individual, and there exists something so that the overall error term can be minimized. And this is in the form of a look like a Jamestown estimator, even though we haven't really drawn connection with empirical base yet. And this is this gave us a very nice result of using this guidance to develop a early stopping rule for the algorithm. So everything together, that this is really a very super quick calibration step, and then this is update, and then we were tracking the using another loss function to help us track the progression of the calibration. So in this algorithm that we implement this, and then we evaluate the calibration in several ways. We'll look at how the raw prediction perform and how the calibrate perform by offering the labels in terms of both the y and its distribution. So how much time do I have? Okay, so one thing that one reviewer asked us a very good question, because they're trying to understand what the calibration does, which challenged us to create this visualization. This visualization is the empty dots are, each of this is a simulation study. And this simulation study has mean square error of this value and then correlation, rank correlation on this value. If you recall the visualization I show, where the y and the y hat are associated but not linearly correlated, meaning that you are systematic biased from y hat is biased from y in a systematic way. So you have explosion of mean square error, but somehow the correlation is correlated using rank correlation. And then I actually have a discussion with some other researcher does scientific modeling, such as like using statistical models. They often see the residual. Sometimes you see the prediction does trace the true value, but sometimes falls short in the tails because the distribution is not calibrated. So this just shows that for each of the study, when we do the calibration, we're not changing the rank correlation. That's why the line goes forward. But because of our shrinkage towards the collective shrinkage based on the distribution alignment, that the mean square error actually reduces. And then you can see that they all return to a line where the mean square error and correlation become associated. And so we apply this to a real climate model, but a simple one idealized, because this way we can run a lot of experiments. And this is in ocean turbulence, it's called eddies. It's just the way the water swirl around. And this simulates that dynamic. And then we applied for the parametrization part, because in the ocean physics, they have the result part. They actually celebrate that equation a lot, but they worry about that the grid is too big for the equation to be accurate. So the machine learning was applied to generate that. And then so in their results, they found that the mean square error was actually rather accurate, but when they go online, they do the kinetic energy, some other energy, and then they were looking at this around. So the blue curve is the perfect ground truth situation, is where if you have a high fidelity simulation, what that energy should look like. So that's what they regard as gold standard. That's where you want them to be. And then the other one is the orange dashed line is when you apply the low resolution simulation using the same equation. Remember the first slide I said, just throw away the unresolved, apply the resolved directly, and you can see a big gap between the energy spectrum. This shows that it's not simulated the same kind of dynamic. And you can see here we are considered 3 methods. One is applying a fully convolution neural network to replace fully machine learning. The second one is no machine learning, just calibrate the low resolution using our proposed method. The third is a combination of the two. And then you can see that the purple is shows to a various extent improvement, somewhere substantially along certain energy, and some of them moderately. And then the interesting thing is that you can see that the red line is even without the machine learning. So the biases exist in the y hat, not purely due to the machine learning, but due to the systematic bias of the data. And by considering just one small piece of information is marginal distribution, you are able to improve the not only the prediction but also the spectral behavior of this. And because the curves are very hard to track, we applied the scores developed by climate scientists to measure different methods. So here, for each of the graph, you calculate the mean square difference between the curves, and then you aggregate the curves between the compare the model to the high resolution and a baseline model to a high resolution to see how much improvement there is. So to read this, the way is that the red color indicating that our calibration improve above the model, and you can see that systematically across board, we are seeing substantial improvement, sometimes to more than 50%. Another example that also motivated this is that when we first considered this method, my collaborator was interested in applying the hybrid loss, which is using a machine learning fit model, then using a distribution loss to calibrate. Then we have this example where we do have data that we want to fit between y of interest, but also x variable. But here, we only have very sparse observations, so the distribution is out of the picture. The distribution of the training set is not reflected in the overall distribution. So this is about the PCO2 fluxes between ocean and the air, and then globally, there are only 1% to 2% observation available. So the direct learning is you will take the predictor to the target variable, and then you input, these are the input variable, and then you have a vector of 16 y variables in different regions. The postdoc and doctoral student and postdoc of my collaborator created something called testbed. They use a lot of Earth system model to generate a lot of what's called reanalysis data. You only have one Earth, so sometimes it's very hard to evaluate the method using the real observation. But using climate system model, you are able to generate full coverage, high fidelity simulated data for you to verify methods. And here is the third data set. Remember, you have Kilsbench, Clemson, and here is called the Large Ensemble Earth System. This contains 100 members of the models, but they have full coverage of the ocean for you to experiment sparse data sparsity issues. And here, what we found, I'm gonna skip the further workflow. I want to show this. What caught my attention was they were evaluating the predictions, and then here in the panels is that this is a pattern correlation. This is the error term, the mean square error, but also this is a correlation. So what I found is that you have places that have substantial error terms, such as here, but also can have very high, the other way around. I think where is it? They can also have very high correlation, meaning that the prediction is systematic bias contributing to the mean square error. So we identify a region with substantial missingness, a lot of zeros, and then applied the machine learning method and then our calibration. And this is to show that the assumption of a common knowledge distribution is not so far-fetched here. This is a distribution of the temperature over the years, even though you see a shift, but the overall shape, no matter how much change, the shape is similar. So it's reasonable for us to assume some historical data should be able to give us the knowledge distribution. And we apply the calibration to show that the calibration, which takes the orange curve from the knowledge average of previous years, we're able to move the blue, the raw prediction, closer to the actual ground truth of the distribution. And to summarize that, this overall performance, and you can see that the both mean square error and the Watson distance, that the proposed method shows substantial improvement. Here, we're being 100% transparent, is that a lot of that can actually be addressed by a normalization step, by moving the distribution by mean and standard deviation closer to the knowledge distribution. But this is to show that the calibration step, a single calibration can further improve the results. And this is overall, and then even if you break down by individual month, and then the performance is rather consistent across all the months we have taken taken a look at. So to summarize that, we proposed a different approach of thinking about how we can address a distributional discrepancy between a predicted outcome against a knowledge distribution. Rather than using a hybrid loss, we use a calibration step. It offers an alternative approach to leverage such knowledge, and which could lead to more thinking about whether dynamic systems should be modeled using machine learning with a control step. Then future direction, currently we're working on integrating this into a conditional distributional learning framework that you simultaneously project the distribution of the system and the point-wise projection of the system, so that you do not necessarily rely on the knowledge distribution. Thank you.
看看大家有什么问题。
你刚才提到了那个 MMD 实际上是first order，事实上比较新的论文是用那个 K order， 对吧？比如 CMD，你觉得会用 K order 或 higher order 会有更好的效果吗？
我觉得，因为我们现在这个还是在 calibrate the prediction of the mean， right? As we consider more complex prediction， 这个也是需要 consider the extreme event tail behaviors。我觉得 higher order will be helpful。
就是所以你用那个 machine learning 来学那个 big physics model。这个因为在地球系统里，这个 simulation 确实非常费时间。我们也在做海洋啊、大气的。对，就是你现在怎么，因为它是一个 chaotic system， 像你说的，那你是要，so 有 learning is critically depend on time， 对吧？是吧？这个就是我就是想看，因为你最后看那个海气交互是吧？那个二氧化碳的那个海的那个 flux， 那个 model how big is the model？ 这个应该是不是特别大，是吧？
不是特别大，因为它里面有 available 的 variable 并不多。我觉得就是我现在我也还在，这还是我现在正在思考的问题，就是我们 machine learning 假设的我们 statistic make assumption of machine learning 就是 y equal to fx plus epsilon。然后我们那个 epsilon 我们会假设说，就是 of course ideally RID and even though deep inside we know that's not true。那我们进一步会 assume 什么？会进一步我们会 assume 这个 epsilon 是 follow 一个 spatial temporal， 对吧？就比如说我们这边是 Earth system model， 你们会说它是 spatial temporal dependence。但是现在它这种这个 dynamic system with closed loop feedback 的话，这 epsilon 光考虑 spatial temporal 不对的，因为它有可能是 energy conservation， 或者是一些 spectral 的那个 matching。你光看那个 differential equation 的话，你可以说那是个可能是个 chaotic system。但是你 look around 我们这个 Earth system， 其实 fortunately our climate is not chaotic just yet, right? So 它那些那个 energy conservation 其实就是 the closed loop feedback keep the system from going entirely out of trajectory, out of control. What that means is that if the machine learning make the wrong assumption about the error behavior 的话，你可能就没法 truly capture the stable behavior。所以我在想的是，我们 first has assume 我们是 model 一个 relatively stable 的 system， 因为这个 system so far look like even though we have extreme heat, but most of the time 还是 stable 的。所以那为什么我们非得把 machine learning 放进去的话，不用 run 很长时间，它就 entirely become unstable？ 那就是那个 error term 那个它不是那个 main function 的问题，是那个 error term， 所以就要把它想成这个 machine learning fundamental， 就是你现在有这个 input 有这个 output， 这个 input 这个 output 等于 f of 这个的是它的那个 error term， 它不是这么个关系，它是从这边是这个 generate 这个，然后这个 generate， 所以这个是个 mean of that。所以如果你全写出来的话，它的那个 error term 并不是那么简单的一个那个independent 或者 spatial temporal dependent 的那个 structure。所以我觉得这是一个 可能比较有意思的 future direction。
上午那个吴音正好讲过那个就是 ABC 嘛，是吧？因为我觉得这个系统里面很多模拟啊，好像其实也和那个有点关系啊。它那个肯定那个 simulation 非常复杂，也是写不出来一个东西。比如这里面有没有可能有一些这种 hyperparameter 或者这些东西，比如说用吴音讲的那个就是说 ABC 的框架，有没有可能 partially help？
我今天讲的这个不是那个工作，我有一篇 paper 是跟一个 postdoc 做，就是用 ABC 这样 framework， 用 probabilistic programming。Assuming you observe distribution, not the mean. Assuming you observe distribution， 用那个 normalizing flow 把那个hyperparameter 和那个 observation 联系起来的，就其实就是一个 ABC framework， 是有的。然后那样的也有一些，就是我觉得 climate is a place where we can find a lot of interesting data set。
好，大家还有问题吗？
应该用的是 MMD， 用的是 MMD。
郑老师，我有个问题，就挺有意思的报告，就想确认一下，就是那个 U 它是 given 的还是要 estimated？ 就在那 dynamic system 里面。
U 它是用 simulation 来用非常 expensive simulation 来 derive 的，就是你的 training data 是有的，但是 once you deploy it is unavailable。所以它的最后它 care 的不是 accuracy，care 是 whether you replicate the system behaviors。因为你 climate 和 weather 最大的区别就是 weather is about tomorrow's temperature， 明天是多少度 ，climate 是10年以后我们有多少 extreme heat days。they don't care the exact day， 它 care about distribution。所以 climate 是个 distributional learning problem。
那个 U 会和 location 有关系吗？因为整个数据是所有地球的数据。
对，它 U 就是说你的 underlying 的那个 process。如果从 ocean 角度上来说，那个 the process in the middle of the ocean 和 near coast 肯定是不一样的。但是这个the more complicated assumption you make, the more expensive the simulation is。就那个 U 可以是 non-stationary 的。
OK， 好，谢谢。
由于时间关系的话，我们提问就到这儿。我们再次对郑教授的精彩报告表示衷心的感谢。好，下面我们有请下一个报告的主持人。
各位老师好，我是统计系的侯林，很荣幸介绍这个我们下一位keynote speaker, Professor Annie Chu. Professor Annie Chu is a Chancellor Professor of the Department of Statistics at UC Irvine. Prior to that, okay, sorry. Prior to that, Dr. Chu was data science founder professor of statistics at UIUC. And her research focuses on solving fundamental issues regarding structured and unstructured large-scale data and developing cutting-edge statistical methods and theory in machine learning and algorithm with applications in personalized medicine, medical imaging data, etc. Dr. Chu has many awards and honors. She is fellow of IMS, ESA, and also fellow of American Association of Advanced Science. She receives IMS Madeline Award and lecture of 2024, Joe Wallner lecture at 2024, and also recipient of 2025 Carver Medal for IMS. And also she serves as a co-editor of JASA Theory and Methods from 2023 to 2025. She is also IMS Program Secretary and ASA Council of Sections of Governing Board Chair in 2025. So let's welcome Dr. Chu for the talk.
Okay. So let me first thank behind the scene, also the professor in your department. I really enjoy this workshop. I want to give a quick comment. This morning during the panel discussion, the question is like, what is a very key concept that just statistics use, actually widely used large language model or deep learning, but they never recognize. I want to mention, we all know about this transformer, right? We talk about transformer, and the key architect of the transformer, we know the attention, right? That's an article say attention is all you needed for the Vaswani. But we know what this attention behind it is statistic is about model selection. Okay, and almost every one of us did a model selection paper in our field. However, it's like they never really mention, let's say, lasso, SCAD, all this regularization, even Gemstein, the shrinkage method. It's all very, the concept behind the transformer and attention is the statistics. So I want to mention this. Another, before I start my talk, I actually like this. I saw this writing piece of paper stick outside of Purdue University, one faculty. When I visited like 20 years ago, I want to say this. They say, theory is you know everything, but nothing works. And say practice is everything works, but no one knows why. And in our lab, say theory and practice are combined. Nothing works, and no one knows why. So I'm thinking about just like we talk about CS and statistics. So we're doing something like a theory. We claim we know a lot, right? But often that really not very working in the reality. We have to understand what's going on. Another thing I want to mention about actually recently I listened to talk from L.J. Wei. He talked about translational statistics. So this Zhu Suncheng also mentioned that the CS can market well, right? They can do translation. That means often when we give presentation, I also told my students, I say it's all the terminology. Do you expect people understand what you're talking about? People have a minimum background. Do they understand what you talk about? So we have to translate our knowledge that other field people can understand. I think CS is doing better. Okay, that's why the deep learning is so popular. Even transformer people heard about, but do they have the people heard about SCAD, even lasso, right? Lasso maybe it's a lot of citation people know. So I think we have a lot of work to move forward, but still I feel statistics is a lot of hope, so we shouldn't give up. So today I'm going to talk about representation retrieval learning, and we also call R-square. So notice that, so this is actually doing data integration. I still feel like there's a lot of going on in large language model, and ChatGPT seems very powerful. However, when the data has a lot of heterogeneity, a lot of data, it works. Data integration in this situation is very, very useful. So look at the trend that my student, I want to acknowledge, I forgot. So this is joint work with my former student, Qi Xu, on the market this end of year, and I'm very confident he will find a good job despite the current situation. So I want to talk about, let's see the trend. This is starting 2000, and you can see that the statistics in general, we're growing. Well, certainly still, it's like less than threefold compared to 2000. Data integration doing better, okay? But still, I think, let's say deep learning can think about the distribution and also like a diffusion model. This is growing much faster, okay? Lan Wang mentioned about reinforcement learning. This just grows much faster. So, but you still can see data integration have a lot of demand in the marketing and industry and clinical trial or medical science. But the data integration starting really early on. Think about, we heard about the meta-analysis. Meta-analysis, you can see the very early papers by Carl Pearson in 1904. During that time, we don't have a lot of statistics journal, but they have a medical journal, okay? So in Carl Pearson, he specifically mentioned two things, that they have two experience. One's from South Africa, one's from Indian population for the fever inoculation, this kind of experience. They mentioned these two subgroups, that there is a lot of heterogeneity. And also mentioned the South Africa one, I believe the South Africa one, has a very small sample size. And when sample size is very small, it's very difficult to draw definite conclusion, right? We don't, statistical, we say we don't have a power, right? We have a small sample size. And you have other experience, but they're very heterogeneous, they are not homogeneous. So this is a situation that the motivation for doing data integration is really we have a small sample set. We talk about in ChatGPT, we have a large language model, so we have a lot of data. But in clinical trial or medical science, we often have a very small sample size. And also we have heterogeneous, that means the population is very diverse, they're very different. So when you try to do the data integration, of course, there's some foundation behind it. First, they must have some common things you can share, right? Otherwise, how can you do data integration? And also, another thing that when you do this data integration, we actually encounter the challenges is like the heterogeneous. You could have many different type of heterogeneity, not just one kind of heterogeneity. I give you some motivating examples. This looks very familiar. The first one is a minutes data, the handwriting digit from 0 to 9, Arabic. The second image is a K-minutes data, is a Japanese handwriting, 0 to 9. You notice that 8, 8 is just Chinese handwriting, right? And the third image called fashion minutes. It's about, they try to classify, is this pants or trousers or sandals or boots, this kind of called fashion minutes data. If you look at these 3 image data, you actually wonder, can we also do data integration? Can I borrow information from K-minutes data or fashion minutes data to enhance my prediction for Arabic minutes data, right? You think I'm crazy. How could I do this, right? The imaging people, they only focus on this particular medical imaging to do whatever needs I need to accomplish. In fact, there's still, you can do data integration, okay? So first, obvious, you see the heterogeneity. The 3 image looks very different, but the homogeneity, if you, even though from human eyes, you don't see much differences, that's what we need, representation, okay? The representation, I think early on this morning, someone mentioned the language model is the word to vect is a representation. You quantify, right? So in fact, even though it's not can be seen by human eye, still the edges, curves, and strokes, these important features also share among these 2 different data sets, and we try to learn. And we can use this similar representation, eventually enhance our learning for the other data, okay? So in fact, if you do some simple singular value decomposition, but of course, first you need to do some dimension reduction, use a ResNet to reduce the dimension to 512 dimension. And you can, using PCA or autoencoder, this kind of representation method to learn the latent factor. And and here, what we're doing is, I think, mistake, Control L, okay. So if you plot the singular vector for one data set versus other data sets, you find the heat map, which measures their correlation. So clearly you see that MINIST and K-MINIST data share much more similarity. The diagonal, the heat map showing the value is higher, there's a high correlation, right? So you see that they must have something in common, otherwise you will not see this very strong, like around this. And you don't see much similarity from MINIST data and fashion MINIST or K-MINIST and fashion K-MINIST. You still see some enhancement around the diagonal, off-diagonal part, but less stronger compared to MINIST and K-MINIST data. So this tells you, even you're writing in Japanese language or Arabic language, from 0 to 9, there's something you can also share, okay? So this we talk about the heterogeneity and homogeneity using this way, okay? And another data I want to talk about is adenine data. Actually, eventually I also will show you other data sets, but this adenine data is also very representative. So this Alzheimer's disease neuroimaging initiative, this is public available data. All these data sets, you can play yourself. And notice for this very kind of a data set, very interesting part that we have a block missing data. What does that mean? The block missing, let's say this group of subjects, N2 equal to 96. The entire genetic information is missing. This is not surprising. I mean, how many of you we go to see doctor, they check my gene expression, right? Even Wing Wang did a lot of bioinformatics genes, but I never get my genetic information checked, okay? And for the other data source, let's say they are PET imaging or missing, or MI imaging missing. So this is not just complete missing complete at random or even missing at random. Some data set they're missing for a reason. It's observational study. The doctors clearly see there's no need to do this kind of test. They will not force you to do this. They try to save money, okay? So, but the response is a mini mental state examination, which is a measure the Alzheimer's situation, okay? So for this data set, we actually see several types of heterogeneity. First one we call the distribution heterogeneity, and also people sometimes call covariate shift. So if you look at the marginal distribution, so here make it simplify. I just use the first PCA, plot the first PCA versus second PCA for the first data source, which we call N1 equal to 69, the first data source. This is every observation is observed, okay? And the second data source, N2 equal to 96, with one gene expression variables, about 300 variables, they are missing, okay? So if you look at a different source, source 1, source 2, source 3, they have a distribution shift. The center is different, and the spread is different, okay? So this is one kind of heterogeneity. And we also can look at association between the covariates information, the association between covariate and the response. This is sometimes we call conditional distribution of response given covariate. This could be also heterogeneity for these 3 different sources. So here the different colors from different sources. This is about 50 covariate information, and it's showing that some is positive, some is 0, some is negative. So you can see the association between the covariate and the response across different data sources. They could be heterogeneous. This we often call posterior drift. Although this had nothing to do with Bayesian. So when we submit paper to the journal, they say, oh, what is your pry? So so you talk about posterior drift, actually nothing to do with Bayesian. And the third type of heterogeneity we call observation heterogeneity. So this is based on, because you have observational study, the missing data is just by nature behave this way. And this we call observation heterogeneity, okay? So the question is, can we integrate what we call multi-source, multi-modality data to train a prediction algorithm which can accommodate this all different distribution or posterior or observation heterogeneity simultaneously? Someone mentioned that I want to do some unified framework, not just like I can use this method just for this particular data only, okay? So this is some literature, although there are a lot more literature on this heterogeneity. For example, distribution heterogeneity, they kind of assume them a partially shared structure using the joint and individual structure, something common, something different. And the posterior heterogeneity, this is like a lot of work going on in transfer learning or multitask learning. Sometimes people also call domain adaptation, and also optimal transport is also in this kind of category, okay? So often this requires the same model for different data sources. And observational heterogeneity, people try to impute the missing value. The most work is, I'm just impute. But notice that if you have entire blocks, 300 variables, entire blocks are missing, how can you impute them? You pretty much made up the information which is not valid, okay? So we mentioned this missing data could be very intricate in a sense that this source of data, the correlation structure, is very different from the correlation structure from the other data source. So if you assume they are common, you can do imputation, but otherwise you cannot really, the imputation will not work, okay? So so far, most existing data integration can only accommodate 1 or 2 of this kind of heterogeneity, but not all of them, okay? So here's what we try to accomplish. We try to build a unified framework, what we call the representation R². Okay, it's different from a coefficient of determinism, which is traditional R² we talk about. So what we can do is like we can accommodate this flexible sharing structure. What we later on will discuss, it's a partially share. We don't need to fully share among the data source. And this can handle this distribution heterogeneity. And second, we can do the data source specific learner. That means for this specific data, I can learn the learner and to predict what's going on. Okay, this allows us to do posterior heterogeneity. And also we have this modality-specific integration in this block missing problem to accommodate this observational heterogeneity. And we try to talk about the new penalty we call SIP, the selective integration penalty, okay? So this is the problem set up. We have each source of a data. We have a different source of a data. Each source, we have a covariate XS. We have a response YS. And here we allow all this heterogeneity across different data sources. The marginal or the covariate information can be distinct. That means for this data source, you could collect a certain covariate which is not observed by other data source. And also we can accommodate this posterior heterogeneity, means a conditional distribution, y given x can be different. And third one, so we allow this observational heterogeneity. That means you have certain data source, only have a partial modality. You don't have the complete modality. The goal is try to learn the data-specific learner FS, okay? So let's first talk about how can we do this for this distribution heterogeneity and the posterior heterogeneity using the R squared. So this is the overall method review that, so on the left side is my hypothetic, the true data representation. And often they're unobserved. You have observed the data, but the true data representation, we don't know. So for example, I can measure a lot of things about a person, your hair color, your race, your gender, your age, your BMI, all this. But however, a lot of things I don't know. What is your personality, right? What do you like? What's really in your mind, right? These things are very difficult to learn, right? So what we call this representation, when we try to learn from this data. So you notice this is 4 different data sources. We have something could be shared, like a blue color, shared by both data sources. But certain features only by itself. It's very unique for the data source, let's say 3, the dark green color. It's only in data source 3. So the middle one is that we collect all the unique representation and we put this as a dictionary. Okay, it's like my library. I collect all this feature. And when I do this data source specific learner, I try to retrieve the information I need. So it's a lot more flexible. So if for this source 1, I need all this 4 different color, so I need to retrieve from my dictionary. Now notice the right side color, the blue color, is not the same as the blue color in the left side. The reason because after dictionary, I did some integration. So therefore the blue color is learned from both V1 and V2 source, not just learn from one data source, can learn from multiple data sources. Whatever the data source have this kind of feature, I can learn. And I retrieve this and for this source 1, source 2, source 3. So I can borrow information from other data set. Okay, so this is kind of the key idea. So this is what I'm just saying, that we have the dictionary, and we know certain representers are fully shared. For example, the light green color is fully shared, but some is a unique, the dark green color, and some is a partially shared, the blue color. Okay, you might ask how we learn these representers. There are many ways. Like statistics, we using the PCA. So this is another thing I think they kind of don't mention too much about principal component, which is very useful in deep learning, right? The principal component is a linear version of this autoencoder decoder. Autoencoder decoder is a nonlinear version, but the same, very similar concept about you learn the latent representation from your data, okay? So I'm not going to give you a lot of details. How can we learn this representative, but you can use it PCA or neural network can all be employed, okay? So this is a motivated paradigm in contrast to the existing method for the data integration. So we all know this story about blind man touch the elephant. We always criticize a blind person is a very narrowly limited scope, can only touch the things they touched, right? So they don't see the entire picture of the elephant. But today, actually, I'm talking about the opposite. So here, when we do data integration, I say I don't need to learn every feature. I don't need to collect every features of the elephant. If I have to get every feature of the elephant, I can only use the data from the elephant. And if the elephant, the subjects, the number is limited, I can only use a handful of elephant. On the other hand, we believe the other data set share the similarity with the elephant, right? The rope, the trunk, the spear, the fan, and all this wall, right? So therefore, that I don't need to use exact elephant to learn, but I can use other data sources to learn some similar feature with the elephant, okay? So this kind of full-sharing structure with a partially structure is a contrast. So I have a lot more data sets to use if I just only assume partially shared structure instead of full shared structure, okay? So the integrativeness is much more adaptive. In contrast, it's a fixed structure assumed for the fully shared structure, okay? And by the way, this is me with the elephant, so not real elephant, but this elephant actually, anyone knows, in Manhattan City. So Tian, you should know. You know that? It's in Manhattan. There are several elephants distributed in Manhattan. It's a sculpture made of the wood. So maybe they removed this already, okay? So here's the representation retrieval part. We had the dictionary. You learn from the representer. So for each data source, we need to, this is a representation retrieval matrix, which is a kind of binary. If this feature I need it, I put a 1. If I don't need it, it's a 0. Very straightforward, okay? This is called representation retrieval. So first, this also provides this interpretation. Someone mentioned about trustworthy machine learning, interpretable machine learning, that here, even we learn, we don't understand why, we just retrieve. But here, actually, we have a representation retriever. We know which representer we retrieve. That's also useful, okay? And also, we notice that for here, first, it's a binary. We're going to talk about this later. And second is about this some representer is much more retrieved more often compared to the other, okay? For example, the second representer was retrieved 3 times for 3 data sources, but the last representer is only retrieved once, okay? The dark green color. So how can we accommodate, how can we model this? We notice that some representers used more often, more frequently compared to the other representer. So here we propose the SIP penalty. Okay, that's the emoji of the SIP. And also I like the SIP because remember we all read the Qin Yong's novel, right? Qin Yong 小说. And the 西功大法, right? So this is like, but I always think about whenever the Qin Yong, it's like you should only SIP the useful energy compatible to you, not just some is a very negative energy, right? So this penalty is quite interesting. We're showing this, I can explain this easily. So if this representer are retrieved by all data set, now if you look at this double summation here, if the representer is retrieved by every data set, the double summation will end up to be S. S is the number of the source, okay? Because every source has this representer. Then therefore, the right term is equal to 0, and you take the minimum, that's 0. That means in this situation, you will not do any penalization because this representer is so useful. Every source uses it. But for some other representer, it's very unique. Let's say it's only used once. Then all the double summation end up 1. So therefore, the minimum part was still 1, and you add them together to be D. It's a very large term. And if you do this penalty, that means you will try to penalize. You actually don't encourage this kind of representer that much because it's only unique by one data source, not by all the other data sources. Okay, so this is a kind of key idea of this penalty function. But when we do this optimization, we also run into some practical issue, okay? First, we know this is a binary, and typically we don't like the indicator function that much. It's a non-smooth function, right? And also could lead to NP hard problems, just like a model selection. We don't like to use L0 penalty because NP hard problem. So one remedy is just to try treat this retrieval and learning, just pack as a sparse-induced learner. We'll talk about more detail later. Remedy 2, try to propose a smoother surrogate, okay? So first look at the remedy 1. It's actually quite simple. That theta is your representative you learn, and R is your representation retrieval matrix. It's a binary, right? The alpha is a coefficient associated with all these representers. So if you pack R and alpha become beta. So therefore, it's kind of, you can transform this optimization problem to be more like a sparse, just like when you learn like L1, this type of, this actually showing if the beta is important, then you will penalize less. Okay, the first remedy is pretty straightforward. The second one, we try to smooth up. So original one, remember, it's an indicator. Now, if we try to smooth up, we try to connect it to this indicate function. So this is quite useful, called the truncated L1 penalty. I think early on, Xiaotong proposed this. I thought it's very useful. So here we can use this, that you can think about this truncated L1 penalty. It's look like your t-shirt collar. If the gap is very narrow, that means the tau is very small, right? That means you are very close to your original indicate function. Your approximation is good. However, computational is more costly. If a tau is very small, it's more difficult to do computation, even though it's more accurate. If a tau is larger, it's less accurate, but easier for computation. So translate to this SIP penalty, looks like this, a right figure, okay? So if you have only unique represented, not shared by others, you have to do penalization. But any represented, if it's shared by other, you're going to penalize less, and it's kind of, you're doing this, okay, it's a linear. But I believe there are many other penalties you can borrow. If you want to do some even more fancy, you can do this like a nonlinear, it's faster, okay? So this is how we do the loss function. So the loss function is very generic. You can use cross entropy loss for classification or L2 loss for regression. I just call it loss. And loss function, this is a function of the response and the representer which you learn from your data. And also beta you also need to estimate. So here you need to estimate theta, need to estimate beta, and you have 2 terms of penalty. First, that it's like L1 penalty, like you know how important this beta, whether it's informative. And second penalty is about integrativeness. Some representer is more useful, so you're going to penalize less. So this is pretty much the loss function, okay? So the recap, what we're doing, so you don't know what I'm talking about so far, but hopefully you can remember this figure we call R2 square learning. So original, if you play with Lego bricks, you have many different colors, many shapes, and can think about this representation dictionary. And retrieval depends on your task. If you want to build the car, you can get all the red block, right? Maybe some black, right? And if you want to build a kingdom, animal kingdom paradise, you have multiple colors. Notice this red block can be used for the first task, can also be used the second task. And if you want to build avatar, it's pretty much a grayish color, this kind of shape, you retrieve only this task-specific block, okay, the bricks from this. So this is kind of like what we try to do, the R-square learning. It's a lot more flexible than doing this kind of matrix decomposition, and you end up many possible combinations. This is just you retrieve whatever the representer you need, okay? Let's look at how can we do this observational heterogeneity. Remember, we have this block missing. It's actually quite challenging because when we try to do comparison method, we couldn't find many to do this kind of block missing data. So here's how we use this R-squared to handle this type of data. So for this data, this is for illustration purpose that we don't have any source have all the modality observation. We only have like some just have 1 modality, some have 2, but not all 3. Okay, so how can we do this? So first, representer has a meaningful. So for example, theta 1 specifically represent modality 1 information, and theta 2, theta 3 is very similar for modality 2 and 3. And theta 4, you can think about like interaction between modality 1 and 2. Right? So this means we observe both modality 1 and 2, something synergy going on, we just call interaction term, not necessarily just a correlation, something going on between these two modalities. And theta 3 is like a two-way interaction, 1 and 3, and theta 6 is a two-way interaction between modality 2 and 3, and last one is a three-way interaction. Okay, so this kind of representative has a meaning behind it. So when you look at this, you notice not every representer are identifiable. So theta 1, theta 2, theta 3 are identifiable. That's good because they are observed from 3 data sets. Some is, for example, theta 1 is observed in both theta 1 and 3. And theta 2 observed in theta 1 and theta 2. And theta 3 is only observed in theta 2, okay? And theta 4, you can observe from theta 1, that's it. And theta 5, it's interaction between 1 and 3. It's a gray color because we don't have any data has both modality 1 and 3. And similarly, the three-way interaction, theta 7, it's not identifiable because I don't have a data set have all this modality. But doesn't matter, even some representer is non-identifiable, we can still do the data integration. So here's how we can do this. We learn theta 1 from data source 1 and 2, right? They both have blue color. And learn theta 2 from theta 1 and 2. And theta 3, we can only learn from theta 2. And theta 4, we can learn from theta 1. Theta 6 can learn from theta 2, okay? So notice that this theta 3, 4, 6 can only from one data source, but some representative can learn from multiple data sources. And once they can learn from multiple data sources, you can theta 1, because for theta 1, you need a theta 1, theta 2, which you can learn from SIP. You also have the representative theta 4, you also can learn, okay? So this way, you can retrieve whatever is a representative you needed. So this is for the multimodality with a missing block. And this objective function is quite similar because we try to build a unified framework that the only difference that here we also have summation representing the modality M from 1 to big M. Okay, that's only different things from the previous loss function. Okay, in general, we still have a 2 penalty function here. How much time I have now? 10 minutes, okay. I can go through theoretical. So I want to make the method also has some useful theory, okay? So the question is naturally, do we gain any benefit if we do data integration? If there's no data benefit, we should not waste our time, right? So the answer is yes. So how can you measure you can improve using the data integration? So this is what we call excessive risk bound. So first, the risk bound is defined this way. And excessive risk bound means compared to the oracle one, what is excessive risk you will have? Hopefully, your excessive risk is as small as possible, okay? So here, when we do data integration, 2 things we need to consider. One is the number of a data source. You imagine that if you have a more number of a data source, you think you will help you improve, right? So this is the gamma part. So the gamma part, you see that's a greater equal than eta. So eta is kind of low bound for the number of a data source. I don't know, I just need use a theory to establish what the low bound would be useful. The other one is about the approximation error. So because there's a lot of approximation part, first when you do representer learning theta, this is try to learn the function space. Typically, it can be used as red metric complexity. You see how complex this function. If a very simple function, you can use a very simple representative to learn. But if it's very complicated, you have to use the larger number of the representative. Actually, I want to mention this is connected with double descenting. So people someone didn't mention the old days we believe in Bayes-and variance trade-off, right? And double descending part, this part seems to disappear. It's a contradict to what we learned from our textbook. So you're overfitting. After doing this, you're going down, right? This is actually the reason because we talk about different things. And the different things are because this is a functional. If you can, even that they're overfitting, still then when they try to approximate this function space, they're using much simpler sparse represented to approximate the function space. So therefore, even though look like overfitting, they can still reduce the error part. It's due to the functional space, okay? So here the theory part. So excessive risk bound is bounded by several terms, 4 terms. I'm going to give you quick what this is about. The first term is about about the complexity of the learning representation. The second term is about cost of approximation, right? So you hopefully you can characterize the complexity well. You also want to reduce your cost. The third term and fourth term is a very usual one about the cost of learning data source specific learner, and fourth term about the complexity of the learning. So you notice a few things I want to summarize. One is the lambda 2 is a tuning parameter. And if we have a large penalty for this SIP, it's a lead to a large ADA. That means I encourage more data integration. So ADA is large. And also the pi is smaller, okay? So this can help us improve the convergence rate. Okay, the first. But you also need to be careful. It's a double-edged sword. That lambda 2, if you're too large, you could also incur the overfitting problem. So you want to balance it's a tuning. And the second part is about the tau. So I want to mention this penalty function. Let me go back quickly. So the tau, remember, when tau is very small, the approximation error is small. It approximates well. But the computational cost is large. Because once tau is close to 0, it's just going to similar problem like MP hard problem. So therefore here, the tau is also for this, play the both first term and the second term. It's also kind of, I go too much, okay. So it's kind of like in one term, it's a monotone decreasing. The other term is a monotone increasing for the first, second term. It's the opposite. So you also need to find the optimal one for tuning for this tau, okay? But in general, telling us that if you do data integration, if the cost, you have to compensate your data integration cost. It's like when you do transfer learning, you have to be careful about doing negative transfer. So here, you need to be careful that your benefit have to be play bigger than compared to your loss, okay? So I will play the real data, so it's very interesting. This is called pan-cancer data, which have 5 different cancer. They're collecting, each clinician collect their own data. So one's a skin cancer, then colon cancer, and lung cancer, pancreatic cancer, and breast cancer, okay? 5 very different cancer data. The question is, how can we learn from one data source to the other data source, right? First, they have all the heterogeneous, that the marginal distribution are very different. The tumor size is very different, and what kind of the data they collected could be all different, right? So we have both covariate shift and posterior shift. So let's look at this R-square learning result. You can see you measure this mean square error. All the other methods, some is the computer science developed. So I want to mention with statistics, we also had an advantage. A lot of methods we compare is from computer science. And some is individual learning, which actually is not the worst sometimes. Individual learning just learn from this data source alone. Some pooling, just doing naive pooling and do that very simple data integration, get a result. You can see for the skin cancer and also pancreatic cancer, the mean square error is all below 0.1, much better than other one. You might wonder, what is the foundation? How can we do data integration for 5 different cancers? So I think we probably know this better. There's a genetic, something's very unique. Like the breast cancer, the BRCA1, BRCA2 is very unique for the breast cancer. But there's one gene called TP53. It's actually kind of this, if this gene is abnormally mutated or did something badly, it could affect all kinds of different cancer. So therefore, even though from this data source, we don't know exact things they share or not share, but through the representation, learning or retrieval, we can borrow all this information together, okay? The second one is about the adenine data. So we assume they have 4 different sources because they have missing patterns are very different. And look at this mean square error. If you're using block R² method, all these are better than individual learner, and the other ones that discount, they try to impute, which actually not doing well for this data set. It's even perform worse than individual learning, okay? So for each data source, we are doing better. So summarize, so today I talk about a unified framework really for heterogeneous data. We talk about 3 kinds of heterogeneous data. And this key ideas about the R² and try to retrieve, provide this interpretable, the sharing structure, okay? And we talk about selective integration penalty, try to encourage the integrativeness. And the block representation retriever also able to help us to address the observational heterogeneity. So thank you for your attention. If you have any question, yeah.
Thank you, Dr. Qu, for the great talk. Is there any questions?
Yeah, Minge.
I have 2 questions. The first one is that this is a machine learning method. Typically, when people are doing the meta-analysis, you have inference. So whether your group, you guys have think about the extending this to have inference of the results. That's one of them. Yeah.
So Minge asked a question. We so far we haven't worked on the inference. I know Minge did the confidence distribution. It's a kind of fusion learning. I actually just listened to Regina's talk. So in her work, they particularly address the uncertainty and also the inference, build the confidence for the heterogeneous data. So I think what we can do, like using conformer, I think because it's easier to use conformer prediction, but I think I also think confidence distribution, CD method, might also work. So we haven't done the inference part, but it could be the future work. Yeah.
Yeah, really nice. The second question is that your first example is a little bit very drastic. So I'm just wondering if that handwriting things, right? Those numbers, if I use, well, I think it's 5 by 5, 25. I just, maybe the last adding an additional data set. It's just 25 kind of whatever random images. Will you still be able to learn something? When you learn something, you must have some sort of common things, right?
Yeah.
So is any limit from there pushing? I know your genetics data, that makes sense, but it's easy.
So image data. So actually, I didn't present the result, but the result showing that we still able to learn, let's say, from Kim minister, even fashion minister, to enhance the prediction for the minutes data. So this is what I mentioned, like for imaging data, by visualization, human maybe eyes couldn't tell what the common things they share.
Right.
But still, you feel it's very strange, right? So like what you're really learning, right? So this is like, what is the interpretation? This part, I think it's a very interesting question. Like for the genetic, we can explain what's the science behind it. Right, but for the different image, I don't know, maybe someone from the audience, I know, I think maybe it's already, oh yeah, I think Sun Lao is somewhere. Yeah, you are here. Maybe you can, have some, say something. When you do the image data, this represent, I would say it's not visualized by your eyes, but still the representer, you learn to vectorize things. It's things there, but we didn't observe, but you can still retrieve, can enhance. In the worst case, hopefully they are not doing the damage.
Yeah, that's exactly. Yeah. Okay, good. Thank you.
Hi.
Very nice talk. I enjoyed. How do you get to the common model? You have a theta x. That's the common part.
Yeah, so the dictionary.
How do you
right.
get that?
So here I didn't give a lot of details how we learn the theta part.
Right.
This theta part you learn, let's say either you can use a PCA, principal component, and try to learn the latent representation, and you can also using nonlinear representation.
So pulling all the data together.
You kind of like, you have to, I didn't give you detail, but it's kind of like you just find a unique feature from each data source and like pull together. It's like when you do language model, we used to call word bags.
So you still learn based on individual data set.
Yeah, you learn from your observed information from each data source. So the idea is that I put in the dictionary. Instead of I put the model as a common things plus unique thing, we feel this is a,
Connection to the very classic topic model, because in the text mining, the topic model, people have different topics. Then when we have the document, people just pick up some topics from the topic pool and put them, cook them together. I think from some point of view, this framework, ideally is kind of has some very similar phenomena, right? But the different here. In the image processing, but we use the deep neural network to learn this representation vector or matrix. So that part is different, but the later part I think shares some similar.
This is a very excellent point. So I think we also currently working on the topic model using what we call the keywords.
Okay.
We don't use anchor words like Tracy doing. You can think about all the words. It's like your small representer. You can think about, and why we have this topic, because this little words compose this topic. So we actually analyze for iClear the keywords. We try to figure out which topic is getting more popular. Turn out reinforcement learning actually going down. But the diffusion model going up. Of course, language model going up, right? But the diffusion is the one shooting up. Reinforcement learning going down. And this will actually learn from the keywords, the topic over the time. Dynamically, they are changing. Okay, so yeah, this is an excellent point. You can think about each keyword is like a small little Lego brick, and then the topic is what the task you want to build. You can find some the parallel connection with the language model and this one.
Yeah, okay, thank you.
Any more questions from the audience? Okay, so let's end this session here. Thank you for the great talk and all the thoughtful discussions.
各位老师，感谢大家今天的一天的倾听。然后下面的环节呢，是由我们的合作单位黄大年茶思屋科技网站 host， 我们集体乘车前往怀柔区，车程大概是1个半小时左右。老师们可以有10分钟的时间去一下洗手间，准备一下大家的行李。然后我们3点15准时在楼下乘车。乘车名单和乘车安排我们已经发到了群里，因为时间仓促，如果有个别